الرحيم. السلام عليكم ورحمة الله وبركاته. الحمد لله والصلاة والسلام على سيدنا محمد وعلى آله وصحبه أجمعين. باسمي ونيابة عن الاتحاد العربي للأسمدة أتقدم بجزيل الشكر والعرفان إلى شركة OMIFCO لاستضافتها لهذه الورشة الجيدة، وهي كانت سباقة سابقا في مجال الصيانة، إذ قمنا بورشة سابقة في نفس هذه القاعة وكانت ورشة ناجحة والحمد لله، ومستمرون بإذن الله للعمل في ايفنتس وورش أخرى في هذا البلد المعطاء في سلطنة عمان. يسرني في هذه المناسبة أن أتقدم بجزيل الشكر والعرفان للأخ المهندس محمد المسروري، وإلى السيد أحمد المرهوبي عضو مجلس إدارة الاتحاد العربي للأسمدة ممثل سلطنة عمان في هذا الاتحاد، لاستضافتهم هذه الورشة ولما قدموه من دعم كبير لإقامة هذا الحدث ليكون متميز إن شاء الله. بالإضافة إلى ذلك أود أن أتقدم بالشكر الجزيل لكم جميعا أولا، ولممثلي الشركات الذين سيقدمون محاضرات وبرزنتيشنز قيمة في مجال المعدات الحرجة في مصانع الأمونيا واليوريا، وهي شركة ستامي كاربون، ADR وتسمكو. بهذه المناسبة أود أن أؤكد أن الاتحاد العربي للأسمدة يقوم بدور مهم في تبادل المعلومات بين شركاته الأعضاء من الخليج إلى المحيط، من الخليج العربي إلى المغرب العربي. هذه التجربة الناجحة نقلت كثير من التجارب الناجحة في الشركات المتمكنة إلى الشركات الأخرى. إن تبادل المعلومات هي الوسيلة المثلى للارتقاء بالمستوى الفني لشركاتنا. اليوم شركات الأسمدة في وضعها الاقتصادي الحالي بأسباب السوق تحتاج منا إلى جهود كبيرة استثنائية لتقليل كلف التشغيل، وبالتالي لتعديل وزيادة مستوى الربحية. هذه الورشة والحمد لله يحضرها 74 مشارك، وهذا العدد جيد لورشة مثل هذه، ومتخصصة في الأسمدة النيتروجينية. أنا أعتقد على الأيام الثلاثة القادمة إن شاء الله ستكون هناك محاضرات من الانترناشونال سبيكرز، وستكون هناك أيضا كيس ستديز من شركتين، وهي من شركات GPIC البحرينية وشركة سافو السعودية. هناك محاضرات في هذا المجال لنقل التجارب الناجحة في شركاتهم حول المعدات الحرجة في شركاتهم، وما عانت تلك المعدات، وما هي السبل التي تجنبنا من الوقوع في هذا الأخطاء. العمل من حيث بدأ الآخر هي مهمة تجنب الشركات كثير من الأخطاء. فنقل معلومة عن وستيد بويلر أو عن HPCC في معمل استطاع نتيجة خبرته الواسعة أن يتجنب حدوث توقف unforeseen shutdown long shutdown غير محسوب وغير مقرر، هذا يعني ومن تجربتنا تلافي توقف للمصنع فيه كثير من العائد. وفي تجارب السابقة وجدنا إحدى شركاتنا توقف لديها المصنع بسبب ال HPCC. كانت كمية الخسائر المادية نتيجة هذا التوقف كبيرة جدا، في حين وجدنا أنه كان بالإمكان لو اتصل سابقا وعلم سابقا ماذا عملت الشركة الأخرى لتلافي هذه الحالة، لكان تجنب من خسارة قدرت بحدود 10 مليون دولار أو 20 مليون دولار كان بسبب ال HPCC، لسبب بسيط أنه لم يطلع على طريقة العمل في شركة أخرى. تناقل المعلومات قضية مهمة وأساسية في هذا. تبنى الاتحاد العربي للأسمدة هذه الشبكة للاتصال والتواصل، ولذلك أنشأ منظومة ومجموعة لكل مجال من المجالات. أنشأ 6 مجاميع خاصة بالصيانة والتشغيل، وخاصة بالسلامة، وفي ترشيد الطاقة، وفي 3 مجالات أخرى في التدريب، لزيادة جسور وخطوط التواصل بين الشركات. كان الاتصال في الشركات على مستوى رؤساء مجلس الإدارة. المفروض اليوم على مستوى رئيس مجلس الإدارة أو اللجنة الفنية، لكن المفروض اليوم لدينا في الشركات ممثلين للصيانة والتشغيل، وبالتالي في 13 دولة 13 دولة فيها المصانع تستطيع أن تجد 13 طريق وآصلة للتواصل مع الشركات الأخرى. هذا انفعل بطرق مختلفة. الطريقة الأولى في المؤتمرات والملتقيات، والطريقة الثانية عن طريق الورش، والطريقة الأهم هي التواصل عبر وسائل التواصل الحديثة الآن لكسب المعلومات. الاتحاد العربي للأسمدة لديه أكثر من 1200 ورقة عمل استعدناها ووضعناها بشكل إلكتروني على موقع الاتحاد. هذه 1200 ورقة عمل تاريخها 40 عام، لكن تنقل تجارب هذه الأسمدة بشكل واسع، وبالإمكان الحصول عليها، ووضعنا لها سيرش انجن، بحيث تستطيعون أن تحصلون على تجارب سابقة. في عالم الصناعة لا يوجد شيء قديم. قد تجد شيء بين هذه 1200 ورقة ينقذ الشركة من مشاكل كثيرة. لا أحب أن أطيل عليكم على حضراتكم، ولكني أقول بأنني سعيد جدا في هذا اللقاء، سعيد لأن أكون في هذا البلد المعطاء في سلطنة عمان، الذي أدعو الله سبحانه وتعالى أن يوفقهم سلطانا وشعبا وحكومة، وأن يأخذ بأيديهم إلى التقدم والازدهار والتوفيق إن شاء الله. وأشكر لكم مرة أخرى حضوركم هذا، وأشكر حسن الضيافة وحسن الاستقبال. وقد وجدت حقيقة في المطار الأخوة من الشركة قد قاموا بواجبهم بشكل رائع يستحق الثناء والذكر، وحقيقة حسن الضيافة وهو شيمة هذا البلد الطيب. أشكركم جميعا، والسلام عليكم ورحمة الله وبركاته.
First session of this year's workshop today. To introduce myself briefly, my name is Thorsten Brandhahn. I'm working for Ode since 2002, and already at that time we're working on the reformers. Well, I have basically still the same job, and at that time My company renamed a couple of times, and so I'm now working for ThyssenKrupp Industrial Solutions, which incorporates the former Ude, but also the cement plant designers from producers and also the TK mining division.
Steam methane reforming is a critical operation and it can be considered as the heart of any ammonia, hydrogen, or also methanol plants. The conversion of hydrocarbons, such as methane, into synthesis gas is a chemically and physically challenging operation. Due to the complex nature of steam reforming, there are many conflicting demands. Hence, ensuring that the process is accomplished both efficiently and reliably, something that involves continuous improvements and the latest technology is available. Today I want to speak about the main trends in reforming technology, briefly introduce our own technology, focus on further options of optimization, of course, like for reformer tubes. And last but not least, environmental regulations makes it necessary to reduce the emissions further. These are also the currently biggest trends in reformer technology. First of all, larger capacities. There are new materials, for example, for reformer tubes, but also for superheater materials, or new materials to resist corrosion attacks, for example, for metal dusting. And of course, increased environmental requirements. So the main trends in reforming technology. One of the main drivers in ammonia industry has been the financial benefits associated with the economies of scale offered by larger plants. Improvements in plant design delivered this over time. In this development process, there have been some notable breakpoints. In the 1960s, the development of centrifugal compressor technology allowed a marked increase in capacity from a few hundred metric tons per day to over 1,000 by 1970. Oh, sorry. There followed a period of steady capacity increase, which had climbed to 2,000 and plus metric tons per day by 2003, which has been, for example, the CAFCO 4 plant built by Ude. The next major breakpoint has been the Ude dual pressure ammonia process. This provided a step change in capacity. The first of this kind was the SAFCO 4 unit with a capacity of 3,300 metric tons per day. However, today, TKS is ready to boost the single train capacity to 4,700 metric tons per day. It's not working. These are some references, some milestone references we have. So the first one is the CAFCO 4 plant. The second one, ZEFCO fertilizer plant with 3,300 tons per day ammonia. Of these plants, we have erected and commissioned in total 4 plants up to today. The latest one is at CFI Donaldsonville in the United States. The plant below this one here, these are 2 hydrogen plants, also built in the United States with a capacity of 100,000 standard cubic meters of hydrogen. It is worth to mention that all the US plants are equipped with an SCR unit. I will come to that later on. But before we go in more detail, I just want to present to you a short overview about the reformer section we are talking about. So that microphone is a bit difficult here. So we have the reformer itself with a reformer box where the hydrocarbon cracking is taking place. We have the penthouse with all the inlet manifolds like feed steam, combustion air. Underneath the reformer, we have the cold outlet manifold system. Then we have the convection bank air preheaters, flue gas fan and stack, as well as on the combustion air side, the combustion air fan, air ducting, of course the reformer again, and on the process side, the secondary reformer, process gas cooler, steam drum, and the steam superheater. These are the essential elements of an Ude reformer, or of any top-fired reformer, let's say. We have reformer tubes, of course, the outlet manifold system, which is a cold one in our case, catalyst inside the tubes, the burners on top, and directly connected to the outlet manifold system, we have the secondary reformer. So the Ude design comprises a cold outlet manifold system. The main components we have here is a pressure shell made of carbon half moly or 1 1/4 chrome material. We have an insulating concrete, and we have an incolor inliner inside. No, it's fine. It's okay, thanks. So the advantage of this system is we don't have any hot pigtails, banded or straight ones. And we are using, since several years, only bubble aluminium for insulating concrete. That is made of artificial raw materials, and product quality can produce controlled much better than for insulating concrete with natural raw materials. So the main advantages of the system are it's maintenance-free, easy installation, you don't have any exotic materials to weld inside, it's well accessible, and it lasts very long. For example, at EBQ 1, it's running for nearly 40 years now, the same system. Also here, of course, we have improvements over the time. So the latest improvement is here a curved inlet band. That is a connection to the reformer tube, and this curved band shall reduce any pressure drop at that location, and shall also reduce any drift for any bypasses within the system. So the next item I would like to present is a secondary reformer. This one is directly connected here to the outlet manifold system from the bottom, so we don't have any lines, hot lines going up to the top. We're going directly inside here. The hot band is within the water jacket, and then we have a riser pipe going up to the top. The TKS burner design, which you can see here, is quite unique. We have an external distribution ring and multiple nozzles penetrating only slightly into the combustion zone. Thus, there are no metallic parts subject to the high temperature in that zone. Since the system is installed, we don't have any failures of any burner here because we don't have any metallic pads in this area anymore. So afterwards, air and process gas are mixing and oxidized partly. Then the gas is flowing through the catalyst bed, through the refractory vault, and here to the gas outlet to the process gas cooler. At the outlet, the process gas has approximately 1000 degrees C and a methane slip of 0.3%, in some cases even less than 0.2%. For safety reasons, the complete secondary reformer is covered by a water jacket. This avoids expansion of the pressure shell and gas bypassing and hotspots. Here you can see the before mentioned optimized burner design. The design of the combustion chamber has been optimized by CFD, you can see. That's not good. The pictures here on the right are showing the temperature distribution at the different burner levels. And you can see that the design is optimized in such a way that the flames or the oxidation takes place in the ring space between the riser pipe and the outside wall. So it's a kind of vortex created here. One second. Coming now to the main focus of this address, further options for optimization at the reformer. Within the reformer tubes, the reaction, so cracking of hydrocarbons, takes place. For this, a lot of energy is required, and the reaction has to take place at very high temperatures in the reformer box. The top-fired reformer has a self-adjusting temperature profile. In case of load and fuel gas changes, no readjustment of burners is necessary, as for example for side-fired reformers. Maximum heat release, so it's here where in the top area where the burners are installed, you have the maximum heat release, and at the same time, you have also the maximum cooling from the inside because of the endothermic reaction within the tubes. So this yellow area is showing the difference across the temperature gradient across the tube section, so outside and inside temperature. And here we have the biggest part, the main part of the chemical reaction inside, and also the main part of the heat, which is released here. So in total, the outside wall temperature is more or less constant over the tube length. With this design, you can ensure a very long lifetime. In addition, the distribution of the burners and tubes across the reformer is optimized in such a way that you have a very good heat distribution across the reformer as well. To understand the potential for any optimization of the reformer tubes, one has to understand the behavior of the tube material in the creep range at temperatures between 900 and 980 degrees C. Reformer tubes are commonly designed for 100,000 hours at given temperature and pressure. So that's one of the reasons is that also the strength data available from all the manufacturers are all based on 100,000 hours. As can be seen here on this curve, generated by Larsen Miller parameters, an increase of about 13 degrees C only from the design point with 100,000 hours would lead to approx half the lifetime already. On the other hand, when you have some extra wall thickness available, the lifetime will increase dramatically. So that's the reason at some UDE reformers, the reformer tubes are running for 25 years without any failure. This table shows the main steps in reformer tube material development. The latest evolution stage of the centrifugally casted HP grade, it's 25% chrome, 35% nickel, is the so-called microalloy R grade. Since creep strength at these elevated temperatures depends on the carbide distribution and stability, tube manufacturers have, over the years, added first niobium and then other small quantities like titanium, zirconium, and of course some raw earth materials to their tube metallurgy. And because of these small quantities, these alloys are called microalloy. The difference between the standard microalloy, which is available since the 80s or beginning of the 90s, and the new one is, first of all, that the new one is optimized for reformer operation, while the first one was also available for ethylene crackers. So, and ethylene crackers have a much higher operating temperature. So for this one, tube manufacturers could, for example, reduce the silicon content. Secondly, the fabrication process, so melting and casting process, has been optimized and is much more precise, and this results in a higher strength of the tube material. So this is the effect of the development over the years. That's HK40, HB modified, and these are the two microalloy parts, where the microalloy R, the latest one, has about 15 to 20% more creep rupture strength than the old microalloy. So with these data, we computed an example which shows the effect of the higher creep rupture strength. First of all, with the calculated design data which we are using today, an HK40 tube would have more than 30 millimeter wall thickness. But that is just a theoretical value, because 30 millimeter wall thickness you cannot cast, and the thermal stresses within the wall would be too high, and that would limit the tube life dramatically. Interesting is the thickness reduction from HB to microalloy R from around 15 to 16 to 11. And with this, of course, the decrease of tube weight. And this would result, of course, in a huge cost saving. For revamps, the replacement of tubes made of materials other than micro R offers a chance to increase the capacity and or decrease the pressure drop. So if you take now HB modified as a reference and upgrade to microalloy, we would end up in a catalyst volume increase of about 7%. Keeping, in this example, the outer diameter the same, just increase the inside diameter. And upgrading from HB to the latest version, you have more than 12% increase in catalyst volume, and with this also an increase in capacity of the reformer. Last but not least, the lifetime of the tubes can be increased. When we keep the same minimum sound wall to be with, in this example, if you increase from microalloy to the latest version, you can around triple the lifetime of the reformer tubes. Of course, that's a bit theoretical value, because Larsen-Miller parameters are not that exact, but that's the number we are talking about. To summarize, the latest developments in tube metallurgy opens many options for the operator for cost savings, revamps, or plant expansions. Coming now to the last topic today, environmental challenges we are facing today. In this chart, I have illustrated the NOx emissions we have been requested by the customers and authorities over the last 1.5 decades. As a comparison, I added also the values for hydrogen plants, which are here in blue. The 3 plants with 200 milligram per standard cubic meter are all in the same country and are more or less the same plants. But what you can see is that over the last years, especially over the last 5 years, the allowable NOx emission level has been lowered dramatically. In green, I added plants we are working on right now. So we have, of course, still plants which have a quite high level, but also plants which are also here in the region less than 10 ppm NOx in the flue gas. As a first option, I will talk about the use of the latest burner technology. These burners are called ultra-low NOx burners. The performance of the burner itself is of course affected by several process parameters as shown here, especially combustion air temperature and fuel composition. The different burners available in the market can be classified into air stage and fuel stage burners. For each type of burner, several reaction zones will be created, which will lower the flame temperature and therefore reduce the thermal NOx created in the flame. In addition, ultra-low NOx burners can be characterized by the significant flue gas recirculation. So a part of the flue gas from the burner will be re-entrained into the burner itself, and with this further significant NOx reduction is possible. However, a further reduction will be more and more difficult because next to the thermal NOxes which will be created within the flame, you have also chemical NOxes, and these we cannot avoid. Oh, what happened here? So that is the state of the art in burner technology we have. For ammonia plants, basically air stage burners are going down to 90 milligrams, so around 44 ppm. Fuel stage burners, the best you can have actually is 80. That's around 39 ppm. Of course, this depends on the surrounding conditions like fuel and air temperature and so on. So, in order to achieve NOx emissions lower than 90 or 80, which we have shown right now, which we can do for the burners, one has to install an exhaust gas treatment, a selective non-catalytic reduction or a selective catalytic reduction. The difference is the existence of the catalyst and the position of the ammonia water injection. Ammonia water is typically used for this unit. As an alternative, one can also take a urea solution. Yeah. The advantages of the SCR, the with catalyst, is the lower consumption of ammonia water, which is not a big problem for an ammonia plant, but maybe for hydrogen plants it would be a huge benefit. Then you have higher NOx reduction rates, up to 95% for SCR, compared to only 50% for an SNCR system. You have still a very long catalyst lifetime. And last but not least, the ammonia slip at the stack can be less than 5 ppm. The disadvantages or challenges are that catalyst poisons like chromium may deactivate the catalyst. You will have higher investment cost for the catalyst. The catalyst can be plugged by dust, for example, from the convection bank refractory. That's one of the reasons in Ude plants you will find only concrete at the walls upstream of the SCR unit. And at temperatures below 230 degrees C, SOC can react to ammonium bisulfate, which will be formed directly at the catalyst surface and will plug all the pores of the catalyst surface. So it's also deactivating then the catalyst. But however, altogether, TKIS prefers the use of the SCR system. An SNCR without catalyst would be a good option for a retrofit. This is an overview of a convection bank with an SCR system installed. We have the flue gas coming from the reformer. In this example, we had an additional flue gas coming from an auxiliary boiler here. That's the reason we have two static mixers installed in that convection bank. That is normally not necessary. Here we have an air preheater, several coils. And here we have the ammonia injection grid, where we inject distributed over the cross-section of the convection bank the ammonia for the reduction. And finally here we have the catalyst within this catalyst housing. Of the same convection bank, I have also a cross-sectional view, where you can see that the catalyst is installed in modules and stacked one above each other, and is then simply fixed here to the beams and to the casing. Of course, for every SCR unit, a CFD analysis will be prepared in order to optimize the flow in front of the catalyst. And especially, we need to ensure a correct NOx to ammonia relation at any section of the inlet plane. Otherwise, both the NOx emissions and the ammonia slip at the stack will increase. For the necessary vaporization of the ammonia water, different options are available as a heat source for the evaporation. First, electric heaters, which are commonly used to preheat ambient air. We have used this only once for a very small unit only. A better heat source is, of course, the flue gas inside the convection bank. It is there already for free. We now just need to recirculate it from the convection bank through the skid and back to the convection bank injection grid. And this example is with flue gas recirculation here. And as the last option, we have superheated empty steam. This eliminates the need for fans and makes this kit very easy for operation and also for maintenance. Of course, empty steam must be then available from the plant itself. These are our running references for SCR units. It shows that NOx reduction over 90% is a well-proven design, and also with very low NOx limits, less than 5 ppm. So these two plants at the top are running now for 4 years, and still with the same catalyst, with the first one, of course. So many thanks for your attention. If you have any questions, comments, please feel free also later on.
What happens?
I don't know how this is working. No? This one? This is working?
What happens if you have the case of leakage of the ammonia? in this design, in the latest design?
At the SCR unit.
Yes.
A leakage at what position? Inside the skid or inside?
Yes, inside. You inject ammonia.
Yes.
Right?
Yes.
You inject it through pipes, right?
We have pipes. We have several long pipes
Mm-hmm.
hanging inside the convection bank, and all the pipes have small nozzles, maybe 4 or 5 millimeters diameter nozzles. And in these nozzles we inject the flue gas, which is diluted, or which is diluting the ammonia.
Right. What happens if you have a leakage in the ammonia source? In the pipe itself?
In the pipe itself.
Ammonia will separate, will disperse in the system, and you will find yourself facing ammonia leakage through the whole way.
Yeah, if it's if the leakage is within the convection bank, it's not a big problem, because first of all, the amount of ammonia you inject is very small. So for these kind of systems, we have ammonia components of maybe 20 kilograms per hour.
20 kilograms per hour.
Yes,
Concentrated ammonia.
concentrated ammonia. So with 20% or only 20% in the solution, it's maybe 100 kilograms. So that's the number. So if if the leakage is within the convection bank, it will go out to the stack.
It will go out to the stack.
Yeah.
So you will find how do you detect it? You will find ammonia coming out of the stack.
You have, of course, in the stack a SEM system, so which is measuring the NOxes, CO, and also ammonia. So if there's a leakage which in the convection bank, you will see it at the measurement system.
In this case, you will have to shut down, stop, and fix the leakage, and then start again, right?
Right, yes, but we didn't have that problem so far. And I'm not aware of any problem within the convection bank, because you don't have any flanges there, just a pipe, it's a welded pipe, and a screwed-in nozzle, so there is no potential for leakage normally.
Okay, another question, please. In the last slide, you made the options, right?
For the vaporization, yes.
Yes, for vaporization. You used electric fans, right? And another way of fanning as well.
Yes. Yes.
The last one was the steam, the mini pressure steam. If you use heaters and fans, you will consume it first, right?
Yes, that's the reason I don't like to use electric heaters, because you need a lot of electrical energy, and that's the reason I don't like it. And that's the reason we use it only for a very small unit, which is hardly running. But the advantage is you have fans which are running cold. Second option was you have a flue gas you're using from the convection bank, that you have hot running fans. That can cause some problems with the fans, because they're running at maybe 400 degrees C.
That's it?
Yeah. Yeah, and if you use steam, if you have steam available, it's the simplest option.
Yes, if you have steam available.
Yeah.
Thank you.
Yeah, you're welcome.
Good morning, ladies and gentlemen. I also would like to introduce myself. My name is Reinhard Heun. I'm with Ude and later on ThyssenKrupp Industrial Solutions. I'm with this company since more than 3 decades. Presently, I am heading the ammonia process group in our fertilizer and syngas division. What I would like to do now and today to talk a little bit about optimization options in ammonia plants, and this presentation is related to the optimization of ammonia converters. Ammonia converters, you know, is the heart of an ammonia plant. That's what engineers working in this business very often say about this piece of equipment. I have learned now from Thorsten that there is another heart in the plant. It's the reformer, but also the ammonia converter is an important piece of equipment in an ammonia plant. It's usually the heaviest equipment in an ammonia plant, working under high pressure and temperature and filled with a sensitive catalyst. And ammonia converters are costly. Therefore, it makes sense to utilize the available space inside the converter as well as the catalyst as good as possible. So therefore, I would like to say something about the agenda of my presentation. It deals with the design improvement, better use of the cartridge volume in order to increase the ammonia production. And I will, in the second part, say something about design improvements dealing with a better gas mixing at the catalyst bed outlet. And this will be then closed with a summary. Some words to the ammonia converters, which we as ThyssenKrupp Industrial Solutions can offer to our clients. We are using 3 different types of ammonia converters. They are all of radial flow with indirect heat exchange in converters with 2 or 3 beds. The pressure shell of all types are with a full bore closure, which allows easy access to the internals, and all of them are of cold wall design. There is a 4th converter available, not shown here on this slide, with a final heat exchanger after the 3rd bed, which will be very often used for revamps in older plants when a low outlet temperature is desired. You know, in some plants downstream the ammonia converter, only medium pressure steam will be generated, and then a lower outlet temperature is required in order to match the design conditions of the downstream equipment. How to optimize the existing volume inside an ammonia converter? Let's have a look to the non-optimized design. On the right side of this slide, you can see the first catalyst bed and an indication about the flow through the catalyst bed. It usually comes here out of the tubes of an internal heat exchanger, passes here through the catalyst bed, and goes then here through a so-called dip tube to the shell side of the heat exchanger. And we try to optimize this design in order to get more catalyst into this ammonia converter. And to see this, there is some catalyst, some additional catalyst on top of the catalyst bed. It is not active, and it does not contribute to ammonia formation. It just takes care that after shrinking and settling of the catalyst, that there is no bypass around the catalyst bed. So therefore, there is this settling volume. So how to improve this design? Is there an option to utilize also the mainly non-active settling volume? Based on CFD calculations, we found the following results. First of all, enlarging the inner wall, this one here. Then eliminating the outer wall. So this is now removed, and partly opening the top plate of the catalyst bed. Now the settling catalyst is used from the beginning, and there is no bypass anymore. The flow is then a kind of radial axial flow, and I think that is also known from other engineering companies. Another improvement on a reference ammonia converter, and the reference here is a 3-bed radial flow ammonia converter with 2 internal heat exchangers, is a design without the so-called dip tube. The dip tube is an annular space here around the catalyst bed. And why do we have this dip tube? It takes care that there is an equal pressure drop around the catalyst bed. So by that dip tube and the design of the dip tube and the perforated plates here, they are equally perforated, we can assure that there is everywhere the same pressure drop across the catalyst bed, and the flow through the catalyst bed is unique. A design without the dip tube can utilize this space for additional catalyst. Differentially perforated inner and outer walls here, they take care by the differentially opening of this plate that there is again a unique pressure drop across the catalyst bed. By combining this design with the before mentioned design of using the settling volume, additional benefit in terms of ammonia production can be gained. And I have an example here that is based on an ammonia plant in Egypt with a capacity of 1,200 tons. If you replace the dip tube in the third catalyst bed, you can increase the yearly ammonia production by nearly 2,600 metric tons. And assuming a natural gas price of $4 per million BTU and an ammonia sales price of $350 per year, you can gain an additional benefit per year of more than $500,000 per year. If you do this, enlarging this measure with using the volume or the settling volume on top of the catalyst, you can get more than 4,000 metric tons additional ammonia production per year, leading to a benefit of $836,000 US dollars per year. Of course, instead of producing additional ammonia, let's say the front end capacity is limited, another option would lead then to a lower synthesis pressure. Here in this example, to a lower synthesis pressure of about 1.4 bar, which saves you then some energy on synthesis gas compressor power. Oops. The second part of my presentation deals with an improvement which is related to a phenomenon which occurs occasionally during catalyst reduction or during startup. It may happen that we see during reduction of an ammonia synthesis catalyst, that non-uniform bed temperatures occur. Often it equalizes after some time and the catalyst is completely alive. But occasionally a non-uniform catalyst bed temperature has amplified, leading to a cold and non-reduced catalyst bed segments, while the reduction of other areas are already completed. This here shows, that is from a CFD simulation, and should show that usually, of course, the bed inlet temperature is determined by the heat exchanger outlet temperature. And the lower temperature at the bed inlet, that causes, of course, a lower bed outlet temperature. And inlet temperature to the heat exchanger, and also then to a lower bed temperature. And that effect is amplifying itself, and it may happen that that a non-reduced area inside the catalyst bed remains. And to get rid of it, we found a solution which can be easily installed, but of course not later. That can only be done together with a catalyst replacement. That is a part which will be inserted here at the outlet of the catalyst bed, and it's a spiral mixing coil, and that improves the mixing in this circular room around the catalyst bed, and by that it leads to a uniform gas distribution. We have implemented this coil already in some of our plants in Abu Dhabi, Fertil 2, as well as in Saudi Arabia, Marden 2, and in the two latest plants in the US for CFI. So, coming already to the summary of my presentation. Steady innovations to our ammonia technology, especially in the ammonia synthesis area, will improve continuously the design of this unit. What we have seen today here is better use of the catalyst volume. About 1% capacity increase can be achieved by partly opening the settling volume to the gas flow into the converter bed, and the design without the deep tube also improves the ammonia converter performance. The implementation of the spiral mixing coil, that leads to milder conditions for the catalyst and the converter during catalyst reduction and also during startup. And of course, if there is a cold segment during reduction in the catalyst bed, then with these internals it can shorten the reduction time, and it will also shorten the startup time for any startup. Yeah. Thank you for your attention, and if you have questions, I would be happy to answer them. Yeah, thank you.
Yeah, good morning. My name is Klaus Heinrich, also from ThyssenKrupp Industrial Solutions, former Ude. I'm 25 years with ThyssenKrupp Industrial Solutions, and actually now responsible for the design equipment reformer section for the business unit fertilizer. That means for ammonia, nitric acid, ammonitrate, phosphate, hydrogen, methanol plants. So a lot of equipment, I can tell you. First of all, we want to thank you that we get the chance to present you our experiences we made during the last years with our thin-low waste heat boilers in our ammonia plants. Concerns have been risen by plant owners that our waste heat boiler design is somehow weak or not reliable anymore. Yes, there have been leakages needed to be plugged, or boilers or even tube bundles to be replaced. Sometimes this happens very fast, sometimes after many years of successful operation. There are even boilers in operation since 1989, 25 years without any failure. For this presentation, we want to show you the efforts we, together with you, as our customers, have done during the recent years to find the cause of this mystery story. We believe the results will bring back trust in our waste heat boiler design, which we think is still a very good piece of engineering. I have structured now my presentation in two parts. The first part will give you an introduction. What is our waste heat boiler design? Where are the waste heat boilers located? To get more into detail in this design. And the second part will show you the experiences we made. We made the experiences with Safco, with Fertil, with Maiden, with all the clients in Egypt, which are also present here, of course. And all this is a common finding and maybe a hopeful good solution we come to the end. Very fast, we have ammonia plants with a capacity below 1,500 tons per day, and we have one ammonia converter, which you see on the left side, and we have, of course, one waste heat thin-low boiler. These are single train plants, and many examples of these plants are located, for example, in Egypt. Ammonia plants with a capacity higher than 1,500 tons per day to have two ammonia converters and thus two waste heat boilers in the synthesis loop. You see here the two converters and the two synthesis boilers. These are also single train plants and are located mainly in the Middle East. Ammonia mega plants with a capacity of 3,300 tons per day or higher to have a so-called OT synthesis located between the two casings of the syngas compressor and consists of an OT converter, right bottom side, and another waste heat boiler. This waste heat boiler is horizontal type with baffles, F-type heat exchanger, and is not comparable to the waste heat boiler I will talk today. These other waste heat boilers on the upper left side are vertical boilers. Coming now to more details of the development. Only one slide, don't worry, not every year. The standard waste heat boiler is installed in all our thin loops, independent from design capacity. And it's shown on the right side. It combines boiler feed water preheater, a boiler, and a steam drum in one equipment. This is a good feature because you don't need three single equipments. It was developed already in the mid-80s, not only by Ude, also by others, with its typical fountain-type design tube bundle, which has kept almost unchanged since then. A fountain-type U-bundle, just why is this name so funny? It's like a water fountain. Hot gas comes in, goes up to the heat exchanger tube, comes down like water as cold gas. So this is like a fountain, therefore this name water fountain type. In the middle of the tube bundle, you see here this gray area. This is a so-called intermittent blowdown. This blowdown is necessary to waste water from the boiler to avoid concentration of impurities during continuing evaporation of steam. The water is just blown out of the boiler with some forces by steam pressure within the boiler. There is no pump necessary. And it has a task. It's located very, very close to the tube sheet to get rid here of impurities. Because here is the main collection of this, because it's a vertical boiler. With the development of plants with larger capacities, the ammonia converter was split into two converters, as mentioned before, each followed by a thin loop boiler, utilizing the reaction heat for steam production. A new design, as now shown on the left side, was developed, which in addition is provided with a water cooling system in the tube sheet for preventing nitrating of the tube sheet by the hot synthesis gas. That's also a main feature of this waste heat boiler, that we have in the tube sheet horizontal and vertical boreholes, nearly as many as we have tubes, and the water will be fit in here for cooling down the tube sheet, because we have to be below the 400 degrees, otherwise we got nitrating. With the two-converter concept, this boiler changed a little bit, because now only 20% have been used to produce steam. 80% just goes to the other waste heat boiler, and mainly due to the, not what everyone thinks up here in the waste heat boiler, main of the water goes in during the cooling bores. I show you also some temperatures, typical ones that you get an impression. We normally go in with a two-converter concept and two waste heat boilers with about 170 degrees boiler feed water, steam production, saturated steam 329 degrees. This converter has 450 degrees incoming gas, going of course to the tubes, outlet about 345 degrees. Here we have nearly the same temperatures like the steam temperature, going in through the cooling bores. This waste heat boiler got more warm hot gas, because this is from the first converter. It has about 470 degrees gas temperature, goes down to 370 degrees. We are even able to lower this to 300, 290 degrees nowadays. That means, of course, a bigger waste heat boiler. What are the advantages of these waste heat boilers? First of all, we have no separate steam drum with connecting piping and additional preheater needed. That means low space requirement for layout. We have free movable U-tube design. That means low thermal and mechanical loads on the tubes. And feed water failure does not endanger the boiler tubes. And the heat exchanger tubes made from ferritic material. That means no problem regarding stress corrosion cracking if we have some chlorides in the boiler feed water, which we don't like anyhow, by the way. Other features are tube-to-tube sheet weld by internal bore welding method with full penetration weld. I will show you one slide, just a picture that you see what is this so-called internal bore welding. That means no problem regarding crevice corrosion, because there are no gaps between tube and tube sheets. In other designs, the tubes will go through the tube sheet, and even if you roll them on the tube sheet, you will have small gaps, which will risk later on that impurities will collect there and you get corrosion at this area. And we have a so-called integrated feed water preheating. That means the boiler feed water coming from the right side will be preheated up here. There's an internal shroud, another cylinder in this boiler feed water, in this waste heat boiler. That means the hot gas coming here gets cooled in this area in between there, that we are coming out with a temperature much below the incoming gas temperature, cooling down all this area. Also here I will show you one slide how this looked like, because this is also a nice kind of engineering done here. And as I mentioned before, we have this transverse cooling of the tube sheet by the cooled effluent gas, and we have this internals cooled by the gas. One slide for the details in the incoming chamber.
Sorry.
Yeah.
One question here.
Yeah.
Before we leave to the design of the...
Shall I go back here? Okay.
Before we leave to that, how do you control the gas outlet here in this type of system? I did not work with that one. I mean, outlet gas, the temperature of outlet gas, do we have any bypass tool to control the temperature of outlet gas?
Yeah. Just a moment, he wants to give you the answer. May I have the microphone? Sorry, thank you. It's from the process side. He gives a better answer.
there is always a bypass around this heat exchanger in order to keep the outlet temperature below the nitration temperature.
It's external, you mean externally?
It is an external bypass.
It's
In
not
the
in
two
the system
converter
of the
designs, it is an external bypass, yes.
Okay. There is a bypass separately.
Yeah,
separate
with an
outside of the-
TIC. with a temperature control. It's not shown here, of course.
Thank you.
Thank you. Better working. Okay, give me one slide for the internals. On the left side, you see the central hot channel for the incoming hot gas. The hot channel is not directly mounted to the tube sheet. Hot gas comes in here, goes up this funnel or channel. This is the hotter tube shank of the U-tube, which goes up here. This is the cold shank of the tube from the heat exchanger tube. This area is free, so the cooled gas can all go around here to cool down the hot channel to avoid nitrating. But there's another feature on the right side to be seen. This look here in this detail. This part, we call it false tube sheet. The main tube sheet is here located. It's this one here. What we have in addition, we put into the tubes so-called ferrules. Also to avoid that the tube sheet will be heated up too much. And the connection between the main tube sheet and the so-called fall tube sheet are tube stubs in Cornell 600. They are welded here, seal welded, so this keeps the connection from the false tube sheet to the main tube sheet. And all this is done to keep the temperature of the tube sheet well below the nitrating temperature, and in addition to cool the hot gas channel by cooled effluent gas. Let's have also a look what is internal bore welding. I can present you some pictures which gives you a better idea than words maybe. On the left side, you see the tube sheet itself, and on the top of the tube sheet they have milled so-called hubs. On these hubs, the tube will be placed, and inside the tube will come up from underneath. Here is a better detail. It's a tungsten arc welding torch, and the welding will be done by shielding inside the tube with argon, and outside we have the so-called welding flux, the welding powder located outside. The balls here is just to put them by hand, that the weld flux will not fall into the tubes. Later on, after welding, you have this kind of look. Then you remove, of course, the rest of the flux, and then you have a good access normally, tube by tube, to check it, not only visual. Yeah? You can also do RT tests here. One more slide regarding how it looks like, that you get an impression of size. Again, on the left side, you see the so-called fountain type heat exchanger. Here are the hot part, then goes down cool tubes. Here we have hot-cold design. That means hot gas like this, cold gas goes down here in 4 sections. This is the waste heat boiler number 2. This is waste heat boiler number 1. Here you see a typical picture that it is very important that tubes will be inserted in a certain order, because if you don't do it, you have not access anymore later on the welds. So this equipment is difficult to fabricate. There are not many fabricators available. We have licensed some fabricators, mainly in Italy. And the fabricators need to have good knowledge of the internal bore welding. This is also not easy to handle. During fabrication, a lot of mock-up tests. During welding, every day, every shift will be done in parallel to check immediately, is the welding torch adjusted according to the requirements, is the welding good? And you need also fabricators who do it in a vertical way. You cannot fabricate this boiler in a horizontal. You need a pit, or you need a big hole where you can put it in. On the left side, just a picture. This is the internal shroud, we name it. These are the baffle plates, and you have a look inside from bottom side to the so-called false tube sheet and the main tube sheet, just to get an impression how it looks like. On the right, you see it ready for dispatch, hopefully, right in time. Okay, that was just an introduction for you. What is our waste heat boiler design, to see that it is a critical equipment, not easy to handle. Now I want to present you more about our experiences which we faced during the last years. Beginning of the 90s, leaks were experienced in several waste heat boilers, in single converter and also in 2 converter plants. The information available was very rare. Sometimes only the leaking tube was known, but not the exact location. Sometimes the leak location was near the tube sheet. Sometimes the leak was located in a support baffle location. But all had in common that the leak was due to loss of wall thickness from the outside. This opened the field of discussion. Due to lack of information, a lot of speculations came up. Is it high heat flux at the tubes? Is it steam blanketing at the tubes? Is it insufficient steam exit of the waste heat boiler? Is the water quality bad? Or is it even a lack of intermittent blowdown? All this was discussed vehemently. At the 2004 UDE Users Group meeting, a presentation was held by UDE presenting all experienced damages and put it to discussion. All participants came to the conclusion that there was a clear lack of information about potential causes of the damages, and that a lot more information would be required to get the full picture. As all plant operators stated that their boiler water quality is always good, it was decided to develop a questionnaire to investigate similarity differences in operation in the different UDE plants. You see, we started with a puzzle and hopefully came to a clear picture. What have been the results of this questionnaire? In 2005, a boiler meeting was held at the Ammonia Safety Symposium, presenting the results of the questionnaire, proving that data were not always in the optimum range according to our VGB standard. VGB means is a German standard regarding feed water, boiler water, and steam quality in power plants. We are based our quality rules on this standard. And even if you cannot read the numbers, it's just to see that the red figures means in this plant something was not according to pH control, in that plant it was okay, in this plant again something was not according to pH control we recommend. We have also differences in acid conductivity. And this also with latest evidence of defective boilers which have been discussed, all in common was that there have been deposits on tube sheets. Typical deposits are like this. You see here the tube sheet on the bottom, the heat exchanger tubes going upwards, and here flakes, layers. Later on we knew that these are oxide layers. Also you can see it on the tubes itself. Sieht man nicht meine Maus? Sieht man die? Okay, it's better here. You see here these deposits on the tubes. It's also interesting on the right side where there are no deposits, and this is applied to the tube sheet. There are the firewalls located inside, which keeps the temperature lower. As soon as the firewall ends, we have a higher temperature and the deposits will be deposited there. And what are the failures? Leaks. Also on the symposium, a paper had been presented by the recognized specialists from DSM about damages on boilers, pointing out that concentration factors by evaporation, as well as corrosion mechanisms like first condensate corrosion or flow accelerated corrosion can lead to damages in boilers. The paper came to a clear conclusion: keep your boiler clean and you will not suffer damage. Easy said, but the devil lays in the details. Because what is the problem with the boiler feed water? In 2005, at one of our plants, a boiler feed water preheater, not a waste heat boiler, boiler feeder preheater failed due to tube vibrations. During investigations inside the stainless steel tubes, brownish spots were found, as you can see on the left top side. This is for sure nothing which should be there, especially not inside a stainless steel tube. This was an indication that something is wrong with the boiler feed water and maybe with the steam system itself. At inspections in plant in Egypt, massive deposits on tube sheets of two boilers were found. See the right photos, in the middle and the right left side. One boiler had enormously corrosion damage below the deposits, the other had no corrosion so far. During this time, it was not possible to retrieve samples of the deposits, which looked like spelled off oxide layers collected on the tube sheet and probably also on support baffles. It was decided to execute a study of the whole steam and condensate system at one of the affected plants in the Middle East. This study considered the complete system from damming water preparation to boiler feed water flow to steam production and steam condensate reuse. Each and every equipment was inspected to find the source of deposits. And iron deposits have been found in the suction strainer of the boiler feed water pump and the boiler feed water heater and preheater, and of course even in the thin loop boilers. Finally, a steam condensate line has been identified to be a possible source for these iron deposits. This line was then rerouted from ending in the deaerator and now ending at the water makeup unit for treatment before reuse again. Also, recommendations were given to raise the pH value to 9.5 and limiting the dosing of oxygen scavenger, depending, of course, on remaining oxygen in the boiler feed water coming out of the deaerator. Even if a dosing of oxygen scavenger is almost not required because of low remaining oxygen below 20 ppb, a certain amount of oxygen is always good for build-up and passivation layer on the tubes, especially during commissioning. All these recommendations were taken over to all new fertilizer plants from 2005-2006 onwards. In addition, an automated blowdown operated by DCS, independent from plant personnel, was requested in all new plants. This helps to avoid that blowdown is opened or closed just by accident when the operator is outside and not by a real automatic plan. What are the learnings from 2006? The learnings from the steam system irrigation at several plants are listed above, and a lot of earlier assumed effects of the boil out of a boiler must be revised. Boil out will not remove oxide layers sufficiently. That is the first what we learned out of this. Also, evidence was found that corrosion upstream the boiler leads to iron deposits in the boiler due to the changing solubility when the boiler water is evaporated. This leads to porous deposits in which impurities in the boiler water can concentrate and form local corrosion elements. And more inspections inside the boilers have been performed for further evaluations, as examples shown here. From the different inspections, mainly two mechanisms of forming oxide layers were clearly detected. First, oxide layers are formed during post-wild heat treatment and not removed by boil-out during pre-commissioning. The spell-off later, during operation of the boiler, form deposits on tube sheets and baffles. Under these deposits, corrosion can start by concentration of impurities. See left upper photo for deposition. You see it here at the tube sheet. Bottom photo for corrosion damage. Again, when this is washed away and cleaned, you see here these leaking parts of the tubes. Second source, porous oxide layers can also be formed by deposition on tubes and other iron parts, where dissolved iron in the liquid gets deposited on porous magnetite, which appears as a sparkling surface. When this happens and you go with the borescope, look inside the boiler, you see some sparkling effect. This is due to the light of the borescope, of course, but this is an indication that something is wrong with the boiler feed water. Some iron is in the boiler feed water, which will be deposited. Also, a combination of both effects is possible, as seen in the center photo. The two photos showed spelt of oxide layers, here and here, with additional deposition of magnetite on these oxide layers. Yeah, now what can be done with all these investigations to avoid such depositions inside the boiler? First of all, we made a design change in one of the boilers. As a consequence of the obvious collection of deposits inside the boiler, one of the efforts was to improve the intermittent blowdown. The fountain-type boiler has had already a blowdown, as I showed you at the beginning, but the other boiler did not have had it. Therefore, the standard U-tube boiler was converted into so-called hot-cold tube design. That means the design before, when you look at the tube sheet, hot side, cold side, simple U-tube. Blowdown was located on the side. Here have been the blowdown nozzles in the older plants. We changed this design to a so-called hot-cold segment design. Hot, cold, hot, cold, hot, cold. And we have been able then to put the intermittent blowdown in the wasted boiler 1 over in the middle. All these modifications had the target to improve the blowdown based on experienced corrosion damages under deposits. But this hot and cold design has not been perfect and needed some modifications. I will show why it was not perfect. The hot-cold design as shown here on the slide has a disadvantage for inspection of tubes and also for identification of leaking tubes in case of a leak. Why? This is due to the fact that the so-called false tube sheet, you remember, we have had these hot internal channels, which is below the tube sheet, covers the cold return tubes. And therefore, we are not able to check the cold tube side. This can only be done if you drill holes in this false tube sheet to have an opening to see the hot cold end of the U-tube and to go in with an eddy current testing device, ultrasonic testing device, and so on. We made the procedure also to do it without cutting a hole. That means you do a helium leak test to identify the location of a required to identify a location of a defective tube, and then you know exactly where you have to drill a hole, but this is time-consuming and not really a good idea. Therefore, we changed slightly the design and said the tube configuration was basically kept the same. Look at the left side, but we invented here some covers on the false tube sheet. Underneath the covers are the ending of the hot-cold side, and we can remove these covers during inspection, and we can see the hot parts, which you see here clearly, and when you remove this cover, you can see also the cold parts, and you can identify then easier where is the leaking tube. Even during the hydro test, you see where is coming water out. Of course, we don't want to have leaks there, by the way. But there was another modification we did. From the material samples of spalled-off oxide layers, a clear origin from the post-weld heat treatment could be proven by electron scanning microscopy. Here's just a short description. I will not read it down. What you find when you do the electronic scanning microscopy. But the forming of magnetite is shown on the slide on the left side. You see how it looks like normally here on the left side. As it was not really possible to flush out completely spalled-off oxide layers or remove them during initial boil-out, the logical solution was to prevent its formation during post-weld heat treatment. Thus, all post-weld heat treatment and Ude waste heat boilers were done since 2007 with an auxiliary shell. This is shown on the right side. I hope you can see the yellow. If you have a configuration where you not have a big furnace, some of the manufacturers don't have a big furnace, they have only small furnaces. So interesting for heat treatment is this part, tube sheet shell connection, for example. This is inside the furnace. Outside the furnace was always the tube bundle. In former times, there was no auxiliary shell, we call it, around this tube bundle and also welded here temporarily to the shell, to the tube sheet. This was done, and we have been able to feed in now nitrogen to blanket hole this tube bundle and to avoid any oxidation, any build up of oxide layers. Typical examples you can see here and here. These are very clean tube bundles after the first test of this new kind of nitrogen feeding in this auxiliary shell. All these results of the different investigation and inspections were presented in a paper published 2008 during the Ammonia Safety Symposium. Also no secrets, all things which have been published. So, was it now? Was this the story? Several borescope inspections of boilers in operation during 2008 and 2012 at different plants proved that the condition of the boiler on the shell now was clean, free of spelt of oxide layers and without deposition of magnetite on the tube surface. You see on the left side a typical picture with the borescope and the tube very clean and the wall clean. Yeah, consequently, our paper on this the ammonia users meeting was titled A Story of Success. And now the corrosion problem in the boiler was solved. But it was too easy. You have been too pleased too early. In 2014, a leak was suspected in a wasted boiler 2. This was very unusual because damages on thin loop boilers of 2 converter plants had always affected only the hot inlet side of the wasted boiler 1. As there, the concentration of impurities is maximized by evaporation. Surprisingly, the leak in wasted boiler 2 was not found in the hot inlet, but in the cold outlet tube passes. As you see here, the inner circle is the hot inlet, the outer ring is the cold outlet. Also, the leak were not caused by tube wall thinning due to deposit corrosion. No, instead the leaks were a result of cracks within the tube-to-tube sheet welding seam. This was something new for us. During the root cause meetings at the manufacturers, we have been informed that during the post-weld heat treatment, cracks have been experienced in the seal weld of the auxiliary shell. That means the shell is welded up here to the tube sheet and there has been a crack, and what did they do? Of course, they fed in nitrogen. And the nitrogen was not warm, it was cool nitrogen from the bottles. And our assumption during this time was this affected at the lower part of this auxiliary shell near to the tube sheet, the post-weld heat treatment of tube-to-tube sheet. This fits also with the location of the damages, which have been all on here in the lower part of the tube sheet. This is also the location of the wasted boiler inside the furnace. You look at the wasted boiler. But more, during the fabrication of new boilers in the plant in USA, again during post-weld heat treatment, cracks had been noted on the seal weld. And again nitrogen was fed in. But this time we have had the chance to check the fabrication and do hardness measurements on selected tubes. We have taken the results and the results proved that in sectors of about 120 degrees, which you see here, which is again, if you turn it down, the location how the wasted boiler was heat treated, we have very high hardness values, which of course proves that this is the reason that the cracks occurred in the other wasted boiler during operation. But moreover, also the wasted boiler 1 was of course heat treated, no cracks in the auxiliary shell, but again, we measured the hardness to counter-check it and found again here higher hardness values. The question was now, what happened during post-weld heat treatment? Why do we have high hardness values in this other wasted boiler where we have not fed in cold nitrogen during post-weld heat treatment? The answer is that we have some kind of a circulation, especially when we have a furnace where only one part of the heat exchanger is inside the furnace and the auxiliary shell is outside of the furnace. That means the nitrogen got a slight flow and cools down because the auxiliary shell is not insulated, it's not necessary, and the cooled down nitrogen will go on the tube sheet and exactly at the location at the bottom part where we do the post-weld heat treatment. In order to avoid any influence by thermal circulation inside the auxiliary shell, when it is partly inside and outside of the furnace, it was decided that from now on it is only accepted to have auxiliary shell completely inside the furnace. That means the early stages, 2000, in the 90s, in the 80s, and 2000, it was possible to do heat treatment, either if the manufacturer has a big furnace, complete waste heat boiler inside the furnace without auxiliary shell, without nitrogen. That was the first. Then we have furnaces only part of it. This was before 2006, 2007 forbidden. Then we said, okay, if you have a furnace which has only a small size, you can do it, but you have to shield the outside bundle with an auxiliary shell, with nitrogen feed in. This was now also forbidden because we recognized when we have cracks that feed in nitrogen, we have the circulation shown here on the bottom side. So we only allow nowadays complete heat treatment of the equipment in one furnace with auxiliary shell, with nitrogen feeding, of course, into the shell. And if the shell gets the cracks, it doesn't matter. The pressure of the nitrogen and outside of the inside the furnace is nearly the same. Nitrogen will not disappear immediately out of this casing. Summarizing, for heat treatment, for all future fabrication, it was decided to accept only post-weld heat treatment with the whole bundle, including the auxiliary shell inside the furnace. Furthermore, additional circulation of hot gas through the tube bundle is affected by a temporary internal cone in the channel. We also changed heat treatment and said also hot gas has go inside the U-tubes, that we have a uniform heat distribution outside the bundle and in the tubes. Therefore, we have this cone put in front of the tube bundle. And in addition, hardness measurements will be performed before and after post-weld heat treatment. And mock-up test samples will also put inside the furnace, inside the auxiliary shell, to have comparison values later on. And all this has been done from 2015 onwards with waste heat boilers in fabrication already delivered. One is for SAFCO 4. It's a revamp. It's not a replacement of a defective one because SAFCO 4 has, under my knowledge, no problems with the waste heat boilers with leakages so far, but the capacity will be increased and it's already delivered, and within the next 3-4 weeks they will install this new waste heat boiler. And also Fertil has got a new waste heat boiler under this new heat treatment. Coming to my last slide, the resume of the modifications. In operation, increase pH value in the boiler feed water, as mentioned before. Limit your use of oxygen scavenger, depending on limits in our guideline. Take care to clean condensate before reuse as boiler feed water. Don't make any reuse without proving where it is coming from. Use an automated intermediate blowdown in boiler controlled by DCS. Don't rely on operational personnel. What did we do with design? You remember we have changed the hot-cold sections of the tube sheet, so we have an intermediate blowdown in the center of boiler number 1 now. And we have modified the channel internals so we can better check during turnarounds what is how is the status of the waste heat boiler with eddy current tests. What is important for fabrication testing? We said before obligatory post-weld heat treatment under nitrogen cover with the boiler completely inside the furnace. Hardness tests on tubes are mandatory, and ultrasonic tests of tube-to-tube sheet welds before the post-weld heat treatment is also mandatory. It looks simple, but was a long way to go with a lot of parties involved. And under my impression, if plant operators will keep an eye on the boiler feed water quality and correct blowdown operation, and manufacturers will follow our stringent requirements for quality, then boilers should operate many years without leakage problems. Thank you. The slides end the presentation. I'm happy for questions. Otherwise, I'm available the next 2-3 days. If not, then thank you again.
Okay, welcome back. Good afternoon, everyone. Myself, Rohit Khurana, working in KBR India as a technical advisor. I've been associated with KBR for last 8 years and have been involved in execution of several revamp projects, basic engineering design for the new plants. Today, I'm going to discuss about the KBR ammonia technology, which are creating a difference in the ammonia plant to enhance plant capacity, improve reliability, or improve energy efficiency of the plant. First of all, on behalf of KBR, I would like to thank AFA and OMIFCO for giving us an opportunity to present at this in this conference. The three major equipments which I am going to discuss today are KBR waste heat boiler, second one KBR reforming exchanger system, popularly known as CRESS, and KBR true cold wall add-on ammonia converter. Ammonia plants are facing tougher challenges than ever before. These are due to smaller capacity plants which lacks economy of the scale. The older plants are less efficient, hence the production costs are still high. The equipment, the aging equipment using older technologies, which leads to reliability issues, lower on-stream days, and high maintenance cost. Natural gas supply issues, with each and every day, the natural gas supply is becoming expensive, and also there are some places where there is a curtailed natural gas supply. Some equipments are leading to constraints in achieving more capacity, and also the environmental regulations which are getting stricter day by day. All these issues calls for a revamp of an existing asset by expanding capacity, to improve energy efficiency, to increase reliability, or to reduce dependence on natural gas. What should be the revamp strategy? That's the most important question these days, whether one should use the proven technology or use the conventional methods, which may not provide a value for the money. The piecemeal approach may not provide full life cycle cost benefit. Today we are looking to achieve more and more energy efficiency and by use of the technology. The revamp project goals should it be capacity increase along with energy saving, or only energy saving, or we want to improve the reliability of the plant by decreasing the unplanned shutdowns. All this is calling for a customized solution for each type of plant. Each plant will have different issues. So these kind of solutions are available with KBR for all the existing technology plants. These are commercially proven and viable, and KBR provides a guaranteed ISBL plant performance. So with the help of KBR technologies, we can provide cost-effective solutions to increase plant capacity, reduce energy consumption, reduce steam export, reduce load on primary reformer, or move to alternate energy source. Firstly, I'm going to talk about the KBR waste heat boiler design, the new improved design from mid-1980s, where we started giving this new waste heat boiler. We'll talk about the requirement of the secondary reformer waste heat boiler in ammonia process, type of secondary reformer waste heat boiler, features of our new improved design, and also how can we revamp the legacy MWK design with the improved KBR design. The secondary reformer boiler, the outlet of the secondary reformer is in the range of 900 to 1000 degrees Celsius. It must be cooled to around 350 to 360 degrees Celsius for maximizing the performance of HTS catalyst. Now, the waste heat boiler essentially does this by using the enthalpy of the reformed gas to generate high pressure steam. It can also be used in conjunction with HP steam generation. It can also be used to superheat HP steam. Having subjected to the highest temperature in this ammonia plant, the waste heat boiler is one of the most extremely critical equipment. It must operate on a sustained basis so that we can maximize the on-stream days and improve reliability of the plant. This is how the process of the secondary reformer waste gas is. The steam and the reform gas enter from the top, combustion reaction takes place. In the catalyst bed, endothermic reactions taking place, and the secondary reformer effluent goes out of this, from the bottom goes to the boiler. The boiler is naturally thermosiphon, which is connected to the steam drum from the top. The boiler free water can flow from either top or bottom. It goes to the tube side of the boiler and goes to the steam drum. The second exchanger is optional, which can be either used for superheating the steam or producing high pressure steam. Reviewing the design requirements of this boiler, we see that the gas temperature entering the boiler is 1000 degrees C, which is extremely high, and it also leads to very high heat flux with an inevitable high DT at the hot end. ASME guidelines state that this heat flux will require above normal boiler free water treatment practices. This service is very sensitive to boiler free water chemistry. So if it becomes abnormal, it will lead to corrosive failures of this waste heat boiler. Due to this high inlet gas temperature and high heat flux, the boiler free water fouling will have a dramatic impact. If the steam drum goes dry, the boiler will immediately fail. The process gas side fouling is cyclic and extremely heavy. Also, the process gas outlet temperature must be controlled precisely to maximize the performance of the high temperature shift catalyst. If too hot, the catalyst will be damaged. If too cold, there will be no reaction. Hence, the control must be by means of some kind of a bypass, process bypass. It can be external or internal bypass. Since this service is the most severe in the ammonia plant, it can cause for a plant shutdown. So therefore, the design selection should also include considerations for the ease of maintenance, to allow for quick repair or bundle replacement. For this kind of service, all boiler will probably eventually fail. KBR designed boilers and competitive boiler fail for the same reasons. Common reasons of the failure are loss of water level in the steam drum, which is due to boiler free water pump trip, loss of dilution steam in the feed, which results in high process gas outlet temperature leading to corrosion, or loss or out of spec BFW, which results in fouling. The instrumentation and the controls and the operating procedures are provided to minimize the chance of these failures, but accidents do happen. Coming to the specific failures for the design of this boiler, for the fire tube boiler, it can be failure of ferrule or the fouling in the cold end. Sometimes metal dusting or stuck valve in the internal bypass can also lead to the failure of this boiler. Also, the unreliability and failure of legacy MWK Bayonet design, which I'm going to discuss it also in the next slide. So there are generally three types of waste heat boiler. First one is the KBR design, which was from very old, from before 1988. This was a legacy MWK Bayonet type design. Usually it have three shells, 101C, ACB, and 102C. Probably if somebody has worked on MWK plant will be aware of this nomenclature. The new floating head design, which after 1988 we have provided this design, which have external bypass. It is now we only provide this floating head design. And the next one is the fired tube, which is a vendor design, popularly known as Borsig design. It's a horizontal fired tube type with internal bypass for temperature control. Coming to the legacy MWK design, these have multiple tubes. I can't see it. The inner tubes is known as the bayonet type design. The boiler free water from the boiler free water compartment goes to the inner tubes and comes out from this outer tubes. Thank you. Comes from the outer tubes, which are known as capboards. The boiler free water plus steam goes into the steam compartment and it is connected to the steam drum. The shell of this exchanger is protected by water jacketed with a single layer refractory or the metal liner. Some of the issues with this MWK design was one with the metal liner which will wrap and gets out of the shape. It basically restricted the removal of the bundle or during maintenance time or replacement of the bundle. The water used to deposit at this bottom of the scaffolds, which will lead to corrosion and ultimately the failure of the tubes. And also to maintain uniformity between these two, between the tubes, the nail-like projections were used. These will also cause problems, restrictions in the flow and cause corrosion and fouling of the tubes, and which ultimately lead to the failure of tubes. So from 1950, early 1950s, we have provided quite a lot of MWK plants. In fact, there are 150 plants, 150 plus plants which have this MWK boiler. Next is the vendor proprietary boiler fire tube design, horizontal, which is connected to the steam drum from the top. The process gas is from the side. It is a refractory line channel. It has specialty in tube sheet design and tube to tube sheet joint. The internal bypass is provided for the temperature control, and the process outlet comes from the side. Now, after 1988, we designed this floating. Seeing the issues with the MWK bayonet design, we invented this new design for the waste heat boiler, which is KBR floating head boiler with one pass water tube. The superheater is also quite similar design to the waste heat boiler, but it is optional and can be used if required. Now coming to the features of this new waste heat boiler. The issues pertaining to the MWK design has been basically addressed in this new design. Some good aspects of legacy MWK design has been carried forward. For example, water jacket, and also the water jacket refractory, ease of removal of bundle, that have been carried forward, while some improvements have been made. The difference between MWK design and this design is the one tube pass. There are no inner and outer tubes, there is only single tube. The boiler free water, the process gas comes from the side, and it is unequally distributed between the two ends to control the temperatures out of the inlet to the HTS. The boiler free water comes from the bottom through the downcomer from the steam drum, and there are risers which are connected to the steam drum from the top of this boiler. The shell is still protected by water jacket, but this time instead of metal liner, we have provided dual layer refractory. One layer is used for heat conservation, and second layer is used for erosion protection. The tube sheet at the top is now cold end, while the bottom is a floating head. So because of the cold end of the tube sheet, the failures have been addressed while from the MWK design. The removable channel is at the top, and with this channel removable, we can easily replace the bundle from with a minimum downtime, as if the maintenance is required or bundle needs to be replaced. The boiler free water has the bottom is expansion joint so as to take care of the thermal stresses as well as the weight of the bundle. So this is the internal tailpipe for the boiler free water coming into this floating head section. The process gas, the flow of the process gas side is radial with disc and donut buffer design. So the flow is split unequally between the outlet distributor and the inlet and the bypass outlet. So there are two outlets, one is this one and second bypass outlet. There are disc and donut buffers which basically guides the flow over to the shell side of this waste heat boiler. There are perforated cylindrical distributor at the both inlet and outlet, which basically they are reinforced so that they will not be distorted at the high operating conditions.
There is a shroud in it?
Sorry?
There is a shroud line?
Yes.
There is another additional shroud?
I'll come to next slide. You'll see the impingement bars to take care of the temperatures. So the high temperature coming for the gas, which is at around 900 to 1000 degrees C, in order to avoid directly impingement of the gas flow to the tubes, which can result in the failure of the tubes, these impact bars are placed. These impact bars are placed, which help in also in guiding the flow through these tubes on the shell side. So this is impact bars. Any more questions?
Well, I'm just I want to discuss about the way of removing the bundle from this boiler, because people probably suffer of having the shroud distorted and damaged. Then you will have a problem of pulling out the bundle itself.
So you're talking about the metal liner which was used in earlier designs. Now there is no metal liner. The only thing is there is dual layer refractory. So there is no metal liner which will get out of shape. You can easily remove the bundle in 3 to 5 days.
So you're keeping the water jacket around?
Water jacket around.
And you remove the shroud, the metal shroud?
Yes. Only the dual layer refractory instead of metal liner. In some places, this MWK Bayonet design, we have replaced the metal liner with dual layer refractory as well. This kind of in-between solution for complete replacement of boiler with new floating head design or using the existing bayonet design only with refractory. So we have these total waste heat boilers, 30 plus boilers which we have been using. There are 10 plus waste heat boilers in the new plants which are undergoing engineering and constructions. We have supplied 3 units in retrofit application. It's a well-proven design with excellent process and mechanical performance. But this is our experience with the waste heat boiler. It is worth noting that Sherrit and Norsec Hydro both have the fire tube design, which were revamped with the KBR floating head design. The one of the revamp from MWK Bayonet design to floating head is currently in EPC phase and probably will come online in a year or 2. So coming to the advantage, also would like also to mention this BFPL design, which was the largest plant, 2200 MTPD plant. The 101C has never been opened even once, the floating head design. It has never been opened in last 10 years from the operation. So there are no issues and it is. So coming to the advantages of this floating head design, it is the tube sheet is cold end and water cooled, which is at the top. The tube to tube sheet joints results in a cool joint operating at the boiler-free water temperature, resulting in a reliable design with proven fabrication techniques. Bundle expansions is accommodated with well-proven technology. At the bottom expansion joint is there, which results in zero stresses. This removable bundle design allows the operator to replace the complete bundle with a spare if needed. Typical downtime is around 3 to 5 days. Individual tubes may be plugged if required. Since the control valves are basically in the relatively process gas piping, which are cooler, the valve design is conventional and reliable. So there is reliable bypass control system, not internal type. It is less prone to fouling and metal dusting. Since the design allows for competitive bidding and takes advantage of the global economic conditions with multiple qualified vendors in USA, Italy, India, Japan. The major advantage with this floating head boiler is it can be replaced within 3-5 days. We can provide a design which will not fail. We can provide a design which is easy to fix. So if you see, this is the bundle which is basically ready to inserted inside the 101C floating head. These are the pictures of basically transfer of the shell side of the boiler.
May
Now,
I ask some question?
Yes, please.
When you pull out
The bundle?
outside,
Yeah.
when you bring it back, the bigger flange, now it becomes bigger because now you instead of having shroud, you increase the diameter, of course.
Yes.
Then the flange size will be, and the head flange will be bigger. At the one which is smaller than this one, we're having a headache with reassemble these two flanges. We need a very big hydraulic jet spanners, but we really, I'm just seeing, do you find a way that keep easy connecting the two flanges with the top tube sheets?
The design is such that it completely this channel completely comes out with the bundle, so it can be easily fitted inside the boiler, inside this exchanger. So there is no issues in connecting in the tube, basically putting the bundle down. Also, the design is such that at the normal operating conditions, the refractory and the bundle are very close together, but at the ambient temperature it separates out. So it's very smooth and it can be done very easily using the crane.
I'm just worried about what we suffer of actually is the top flange.
This top flange.
It's with the head, yes.
So
when you make it bigger, it's more difficult to reassemble. So it takes sometimes, the first time, yes, it's good. But with the creeping during the time, there's such a big flange, and you put another additional increase in diameter, then you will have, I think, you will have more problem with the connection.
We haven't faced much issues in this. Probably it was metal liner at your plant which was basically causing problems because of putting in. Ultimately, the metal liner will cause stresses and will lead to more issues. But we haven't faced any issues in putting this boiler down. As I said, in fact, BFPL was never opened, so. Maybe we can talk to our mechanical team, which will basically help in answering your questions. Moving on, so how can we revamp the MWK waste heat boiler? So now with this bayonet design, which is aged and obsolete technology, this is calling for recurring maintenance and failures, which adversely affect the economics of these plants. So to compete with the newer plant, to replace this MWK waste heat boiler design with a new floating head design is a logical choice. Many plants are now following this approach. So before the boiler revamp having 3 shells, this looks like this. After the revamp, all the 3 shells will be removed with a single floating head. These will have external bypasses to control the temperature, so there is no effect on the process. The process remains same, only all the 3 shells have been replaced by single shell. The steam drum and the bulk of the piping remains same at the same location. So this is how the footprint of the boiler revamp looks like. Before the revamp, there are 2 101C ACB and 102C. After the revamp, 101C and CB will be removed. The new transfer line connecting the secondary reformer outlet will be connected to the new floating head boiler design, which is placed alongside the secondary reformer, and 102C can be abandoned in that same place. This is how the layout looks like. The existing 103D, new transfer line to connect to the new boiler. The exit, main, and bypass gas lines are tied to the HTS.
Sorry, I've one question.
Yeah, sure.
The boiler feed water inlet at the bottom, is it directly connected to the pump, or is it coming from?
It's coming from the downcomer through the steam drum. Yes, it's a natural thermosiphon boiler. So the principle is essentially same what was used in MWK design, but the only difference is earlier it was coming from the top, now it comes from the bottom through the steam drum only.
But it's still coming from the steam drum.
Still coming from the steam drum. So how does this economics work out? With the increase in reliability of the boiler, we can increase the on-stream factor by approximately 1.5% per year, which can lead to incremental ammonia production, and hence the payback calculated is around 2.5 years based on NG price of $3.5 and ammonia product price as $400 per metric ton. This is about KBR waste heat boiler. If there are any questions.
One question, is there a limitation regarding capacity? So that means for your larger plants, 2,700 tons per day, is it a single boiler or you need 2 boilers?
For 2,700, I mean the new plants, we generally have the steam superheater. So, but there is only 1 boiler, 101C. There is no 2 boilers. There is no capacity limitation, I should say.
Thank you. I've also a different question.
Yeah, sure.
Do you use this now for revamps only or also for new plants?
For the new plants, floating head design is used.
Okay, then I got it.
Right now, these days, the MWK design has been replaced with bayonet design. One of the projects is in EPC phase in North America. So it is used for both, to answer your question.
Another question is about the floating plate. Above the floating plate, it becomes very high temperature, and sometimes probably metal dusting starts there. How you improve that one? Because I hear that you have improved that one and then you get rid of that.
No, because of unequal distribution between. See, this gas inlet is from here. There is unequal distribution between the outlets. So, I mean, it's not like 50% is going through this distributor and 50% is going through bypass outlet. So we design it in such a way that there is no metal dusting takes place. So
It means you change the outlet so that you keep the outlet down just near the floating.
Near the floating head,
So
yes.
It will cool down.
Correct.
Thank you.
Okay. Next, we move to the CREST technology, known as KBR Reforming Exchanger System. Excuse me. From the beginning of the development of this technology, the watchwords have constantly been simplicity, reliability, high performance, and maintainability. So this KBR reforming exchanger system is very simple, open tube arrangement, which allows each tube to expand individually. So this catalyst tube, this is open end. So it allows each catalyst tube to expand individually. It leads to low stress on the tube sheet and with only weight of the bundle to take care. The single tube sheet at the top also eliminates stresses due to differential tube to metal temperature. This bundle is completely removable, just like waste heat boiler. The tube sheet is located at the cold end of the heat exchanger. The shell is also protected by water jacket along with dual layer refractory, which is also very similar to waste heat boiler design. The catalyst is contained inside the tubes, simple without the use of shell tubes. So it's a very reliable and basically high performance. And maintenance is also basically kept, high maintainability is also kept by having this bundle removable easily. This is 100, basically we call it 100C in our nomenclature. This is the CREST which was installed in one of the sites in USA. So the fundamental behind using this CREST technology is using the high grade heat from the secondary reformer effluent to use it for reforming. Conventionally, the secondary reformer outlet at 1000 degrees C was used for generation of high pressure steam. So earlier, all this heat available was used to generate high pressure steam. But this is extremely high grade of steam, high grade of heat, which can be used for reforming. This is what the concept of CREST lies in. Use the secondary reformer outlet temperature gas, which is at 1000 degrees C, to basically use the heat for the reforming reactions. CREST essentially does that. The rest of the heat is still used for the high pressure steam generation.
May I ask a question?
Yeah, sure.
It looks like that the gas will be cooled down completely through the region of metal dusting. How do you avoid metal dusting there?
It will not be, we generally keep above the metal dusting temperature, so that's how we design CREST for. So CREST, basically there is no metal dusting taking place in the CREST. The temperature is kept above the metal dusting point. So this temperature is still above the metal dusting. So there is definitely not metal dusting temperature. It's worth noting that KBR has the operating experience is only with KBR. It's a KBR proprietary and patented technology which debottlenecks front-end capacity by roughly by 30%. It also leads to improvement in furnace efficiencies. There are milder operating conditions for the waste heat boiler. There is no modification in steam system required for the revamp capacity. It's a robust design, and KBR has done various projects where we have taken the responsibility from the design to the commissioning of this plant. The CRESS increases the reforming capacity by around 25 to 30%, or alternatively, at the same capacity, it reduces the natural gas usage. There are no expensive furnace modifications required if we use CRESS for enhancement of capacity. The high-grade heat, as I mentioned earlier, it is better used to basically generate syngas rather than use for steam generation. The CRESS can be installed while plant is in operation, and tie-ins which can be completed in short turnaround. It reduces severity constraints in a waste heat boiler. The lost steam production, basically due to heat used for reforming, can be replaced using cheaper alternative energy sources or by other efficiency improvements. This is our reference list. Right from 94, this was plant in Canada, which was manufacturing around 350 tons per day of ammonia. Recently, we have done two revamp projects, one in India, Chambal 1, which is 2000 MTPD ammonia plant. This was a non-KBR plant where we installed CRESS unit, which doesn't have any issues till now. In PCS Lima, we recently installed this CRESS unit. I'm going to talk more in details about this Lima unit as a case study. So this CRESS case, basically for this Lima project, we were given the study for this plant, enhancing capacity of this plant by roughly 15% in 2012. We selected CRESS technologies for increase in capacity. The roughly 16% capacity incremental was required. The minimal modification for the primary reformer, minimal impact on the reformed waste heat boiler, and also we had successful installation. So we basically proposed this solution to PCS Lima site. The CRESS island, which was supported by KBR throughout all phases from study till the startup of this plant. During study phase, PCS along with PCS evaluated options and selected CRESS for the study phase. Study phase also included the review of the constructability in already congested area. Secondary reformer, transfer line and CRESS were KBR area of responsibility. Rest were handled by a third-party contractor. We generally name it as a CRESS island, combination of secondary reformer, CRESS and transfer lines. This is how the new arrangement in the model looked like. New secondary reformer, very close coupled with CRESS unit, and during the engineering phase, where we did the basic engineering design, the PNIDs were frozen, the constructability review was completed, model review was presented to the client, and basically HAZOP was performed, and this was finally basically constructed in 2014. In 2014, in 2015, basically new secondary reformer and the CRESS catalyst were loaded. After the catalyst loading, there was around 6 weeks outage for connecting the tie-in points between the process air line, transfer line, and primary reformer transfer line. This is the pictures, actual pictures of the plant. You see very close to what we have predicted in model. The secondary reformer and the CRESS. This is the temporary structure for the CRESS unit, which is used to place the tube bundle. The commissioning of this plant happened in October 2015. Daily operation meetings were held to to take care of the inspection points. Punch lists were used. Performance test was performed in March 2016. The CRESS catalyst reduction took less than 8 hours. No performance issues, all guarantees were met. The production was, performance test run was on 2300 SGPD, and the capacity was not limited by CRESS. The quality of reformed gas on spec, methane slip, and steam import were within limits. Since 2015, PCS have been operating this CRESS unit without any operability issues. This proves that there is no issues with respect to anything. All the considerations have been taken care, like metal dusting or anything else.
Another question. On one of the earlier slides, you have shown that the gas inlet to the CRESS was from an autothermal reformer. So that means it is also applicable for a conventional route of steam reformer and secondary reformer, or is it only applicable for pure ATR plants?
It can be used for both of them.
Thank you.
Since KBR was involved in from study phase till the end of the project, so with the close coordination with PCS, with proper planning and constructability issues, and execution of various activities in the field, it ensured smooth installation and operation of this CRESS island unit. The 3D model reviews also helped in design of this plant in an efficient way without any incidents. So this is about CRESS. If there are any questions. Okay. Thank you. Next, we move to the KBR add-on ammonia converter design, which is true cold wall. Now, it is well-known fact that more the conversion out of ammonia converter, the better efficient plant is. So higher conversion reduces the syn loop pressure and also saves the refrigeration power. Energy saving in terms of syngas power consumption and reduction of refrigeration duty. It can also be used for either capacity increase or energy saving. In terms of capacity increase, it can increase the capacity by 20% or reduce the loop pressure by 15 to 20 kg bar, for 15 to 20 bar. Hence, add-on converter is an ideal way to increase the conversion in the syn loop. So this adiabatic converter in series with the existing converter provides cost-effective increase in capacity and energy saving. The challenge with this adiabatic converter in series is the hot feed inside the hot feed inlet to the converter. As the temperature is around, it can vary from 300 to 400 degrees C coming out of the existing converter. So this converter must be hot wall design. This add-on converter typically has high risk and cost due to mandatory hot wall. KBR True Cold Wall add-on option provides risk mitigation and low cost project. Coming to the issues of the hot wall converter, based on the feedback from ammonia plants worldwide, it is the established fact that all types of hot wall converter are known less reliable with respect to operations, require frequent inspection, and high maintenance costs. Also, they have stringent requirements on the choice of pressure vessel material and type. When exposed to the high temperature hydrogen and nitrogen, the chromoly welds in the chromoly pressure vessel welds are known to have high risk of failure. There are restrictions on the rate of pressurization and depressurization and heating during startup and shutdown, which leads to the production losses. Also, there are restrictions on the feed inlet temperature because of the hot world design, which leads to less optimum conversion out of this converter. Hot versus cold wall is not an issue in most plants having one ammonia converter, but where the feed gas is relatively low temperature, which can be used for cooling the annulus, which cools the basically shell side and keeps the temperature on a lower side. But hot valve will become applicable when second converter in series is used. KBR add-on converter in series, which basically is a true cold wall design, helps in mitigating the risk involved with the hot wall design. In this design, basically the cooling gas, which is from the cold section of the SYN loop, is used as sweep gas for the annulus of this converter. The cooling gas doesn't mixes with the reacting gas. The feed gas comes from the top and goes to either exchanger or it can go directly to the bed depending on the temperature. The product goes from the top. So this is proven vintage MWK design. The design temperature of this shell is same as a normal converter design. This is patented annulus flow feature, which helps in which helps in capacity gain, energy saving, or reliability. Cold wall technology is a better fit, more reliable, and cost effective. The add-on converter inlet temperature can be optimized during the whole cycle because of this cold wall design. The bed inlet temperature can be controlled precisely, and there is no restrictions on the bed inlet temperatures. The cooler shell also allows multi-wall shell, more vendor options, faster delivery, and there are no startup restrictions because of this converter. So basically crux is true cold wall converter is a mechanically reliable converter with the flexibility to increase its operating temperatures. It can provide additional revenue by avoiding costs associated with the maintenance of the hot wall design or replacement, avoiding production loss due to loss of capacity or maintenance shutdown, maintaining sustained production and low energy consumption by meeting specified ammonia conversion throughout life cycle. It can also extend the catalyst runs to the desired turnaround time by optimizing bed inlet temperatures. This is how the typical flow sheet for the add-on converter looks like. The sweep gas is taken from the cold section of the SYN loop, goes through this annulus of the converter, and then goes out and mixes again before the water cooler. So this allows the ammonia converter to basically be designed for a lower temperature. Rest of the features essentially are same as hot wall or cold wall or hot wall design. This is the add-on converter revamp, which was done in CFCL. Basically, before revamp, the production was 1604, loop pressure 208, and ammonia exit converter of 19.6. After installing the add-on converter, the capacity increase was around 10%, loop pressure reduced by 30 kgs, and the ammonia conversion was around 3.5 mole percentage higher. All of this leads to saving in refrigeration power as well as syngas power. The steam requirements for the turbine were reduced by adding this add-on converter. These are our references for the cold wall design. As I mentioned earlier, CFCL, in both the plants we have installed this converter. And the earlier MWK vintage design was in 1960s. The conclusion is basically KBR is a pioneer in revamping existing ammonia plants. We have done 250 plus KBR and non-KBR revamps. It helps in improving reliability and operability. We are always working toward the betterment of the technology. We can provide the solution for specific client requirement. Thank you. I'm open to questions now.
Back to the waste heat boiler again.
Yeah.
You have a water jacket on the waste heat boiler.
Right.
For the energy saving, there is a heat coming on the water, then it goes back to you put additional load on the cooling tower. How you avoid that? I mean, okay, you already put 2 layers of insulating bricks. This will reduce the heat going to the jacket. But in any way, there is a heat going to the water jacket. Yeah. And then there is an additional load on the cooling tower at the end of the story.
The amount of this boiler free water flow through the water jacket is very less. It's only 4 tons per hour of water. Some of the water is used for basically generates steam out of the top shell, and rest of the water is being drained back. So, I mean, for small savings, there is very little potential in taking the heat from this boiler, from this water jacketed. So that 4 tons.
Your original design, the jacket water was going back to the cooling tower.
Okay.
And you feed cooling tower, and you get back water from the cooling. Is in the new design you have the water coming from the boiler fluid water or from where?
From the demin water. Basically, we use demin water. Yes.
And then after you take it back, you will bring it to the.
No, we generally put it into it depends on the effluent waste treatment, because it may have some chemicals like with the iron all over the place on the water jacketed. We put it into the offsites, so if it can be recovered back.
Thank you.
Any questions? Yeah.
Question again regarding the ammonia converter, your true cold wall design.
Yes.
Does it mean that your cartridge has no inside insulation?
No, cartridge has insulation. We want to minimize the heat losses. We want to use it for process rather than dump into the cooling water. The cartridge has quite a thick layer of insulation. Maybe I can add into that. There is only 3 degrees C temperature rise for the cooling gas, which is used as sweep gas. So basically, we have designed in such a way, the insulation is such a way that the heat losses are minimized. We can't avoid it, but we can reduce it.
The entire gas is going through this annular space? Or only part of it?
Only part of it. Only part of it. So the net effect is considerably reduced. Generally, we design it for 30% of the SIN loop flow. Okay, thank you.
Good afternoon, everybody. Today's presentation, I'm going to have a case study of dry ice blasting. I am the first presenter of OMIFCO, so there will be some little introduction about OMIFCO and what it is. This dry ice blasting case study, we have done it handled in last ATR in January 2017. In ammonia 2, we have 2 trains of ammonia. So 1 train last ATR in January 2017. The outline of this presentation will be a little introduction about OMIFCO, and then the ammonia process flow sheet, what we have at the process from the primer former up to the end of the converter. Another thing is the reformer section and the waste sheet section. What this case study what we handled in that the coils of the waste sheet section. The case study, introduction and principle of the case study, and ATR, the convection zone, and the achievement performance after and before this case study had been done, or the cleaning of by dry ice. We have three shareholders: India Farmer Fertilizer Company, OMIFCO from India, 25%, and CRIPCO also 25% in India. And Oman Oil Company is 50%, which in Oman. Plant capacity is around 1750 metric ton per day. This as a design. We have 2 ammonia plant designed by Helder Topsoe, and 2 urea plant also designed by Snarbergetti. 2530 metric ton per day granulated urea using granulator. This is the flow sheet of ammonia. It's using steam reformer. It is designed by Helder Topsoe. The natural gas is coming from the video itself by the normal temperature, atmospheric temperature. This atmospheric temperature and pressure around from 75 to 85 bar from a video from the well itself, from the desert. The primary reformer, we have around 720 burners and self-reciprocating these burners, taking itself without any forced draft fan. It is we have only induced draft fan, and 264 tubes divided in 2 chambers, 132 and 132 chambers. Secondary reformer, we are using process air by HS steam turbine, and we have a waste heat boiler of shell and tube waste heat boiler using steam drum. We have 3 outlet of converter and outlet of HTS, high temperature shift converter, and the outlet of secondary reformer. Then it will go to the shift converter. We have 2 shift converter, LTS and HTS, low temperature shift converter and high temperature shift converter. Then to the CO2 removal section. CO2 removal section, we are using GV with a Gemarco Vitrocoque solution to remove the CO2. It will be sent to the urea plant. Methaneator, and this the remaining of ammonia S200 converter. Then to the separation of the ammonia. Primer reformer. Primer reformer, as I already discussed, the number of tube 264, 720 burners, design side firing design, catalyst, cylindrical shape nickel catalyst. The tube it's around 12 meter tube length, and around ID is 121 millimeter and Audi 146. We have in inlet temperatures are 525 degrees from the first coil, from the flue gas outlet of the reformer. The first coil is around 525 with the steam and gas mix feed to the primer reformer top tubes. And outlet temperature of 770 degrees centigrade. Tube skin temperature design around 893 degrees centigrade, but we are working some less than that, and we don't face any problem till now, any tubes. This is the convection zone. We have 9 coils of convection zone coil. The first 3 from the top, it is a plain coils, and the remaining 6 is the vane type of coils. We have different type of steam coil, NG coil, and there is KBW coil and air coils. This is all the 9 coils from the top up to the bottom. Now we'll discuss the main issue of our case study is the dry ice. Why dry ice? We are using dry ice. Before we use the sandblasting and even we use another water jet to remove that the deposit in the tubes itself. But as we know that the ammonia plant is consuming around 30% of the total one plant, 30% of the fuel is used of the NG, is used as a fuel. So if we can reduce this fuel consumption to the total of plant, so we can save energy and get more production, and so that we use this dry ice cleaning, so to get the maximum production, or we reduce the fuel gas, so can we get some more production. Hydroblasting often used before, we have used it, but the performance was not that much like the dry ice. Technique available including dry ice blasting. It is motivate the fluid to avoid liquid damage of refractory, because normally we are using water, there's a refractory in the side and the bottom side of the wastage section, so it can be damaged. Sometimes it's damaged with the water when we are using the water jet to remove all the dirts there in the. But this technique is improving, and also even there is no that much dirt available. Even can be removed by even vacuum or by remove it. Very easy to remove it. It's not that much affecting the wastage section. The principle of the dry ice. Principle is a device we use to crush the ice pellets itself to small pieces of ice, which use neutralize it by the compressor air, using the compressor air with the gun. This small size of ice is going with the air, and it is deposited in the coil itself, and make it to advance from the surface. It is around minus 78 degrees centigrade temperature. This dry ice precipitates through the deposit material. The warmer surface causing lead sublimation of the dry ice. This is going sublimation, and it is a phenomenon. Normally, it is when it's changing from solid to gas direct without any water, any liquid phase. Sublimation. The gas phase is 800 times greater volume and expand behind the material spin up to remove it, to remove any dust. It can remove paint, oil, grease, asphalt, soot, drain, and refractory dust. The most things that it's deposit in that coils is the refractory dust, and the dust also, and the air dust is coming out from by the burners. Now my colleague Faisal will continue the remaining of the presentation.
Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Faisal Salim Shaibi. I am as an ammonia shift engineer. So I want to thank everyone for present, and I want to thank Mr. Hani for giving this introduction and some more details about the dry ice blasting. So I'm going to continue the advantage of dry ice. The advantage of dry ice blasting is particularly effective at cleaning industrial production equipment. Unlike other type of the media blasting, dry ice blasting generates no additional waste. So, or secondary contamination, even the contact with the surface to be cleaned. And dry ice blasting ability is transferred directly from the solid to the gas, no liquid phase. So this process is known as sublimation, leaving there is no resistance behind. So there is no wasting behind the dry ice. This also makes some ideal of the situation where the moisture is not an option. So there is no moisture can be affected as we have the refractory. So, and as the process is known as ablation leaving, there is no reason behind. Yeah, where the moisture is not an option, it is non-abrasive. The dry ice also, it is non-abrasive, non-conductive, and non-flammable. This is some advantage of using of the dry ice. Dry ice especially effect as reduce the heart of the reach place, reducing to near the assembly of the equipment. So it is no need to assemble the equipment for the cleaning. So we can use it by the dry ice. And dry ice is a superior alternative to the sand blasting, shoot blasting, soda blasting, and water blasting, and or hand cleaning. So there will be some table, we'll talk about this. The conversion between the method we're using in the previous. So we have faced some challenging by using the dry ice blasting. Availability of the dry ice should be closely managed to avoid any melt of the dry ice, to avoid any impact to the environment. The loud noise also required to protect the air equipment and make the irritation to the other people nearby or near the machine or much closer. And effect cleaning can be only occur to the straight line of the side of the dry ice jet nozzle. Sometimes parts can be disassembly to help. If this is directly by using the dry ice jet nozzle directly to the equipment, it may can disassembly the equipment also. Large amount of the carbon dioxide are released, which can be harmful if the ventilation out is in the taking the space. So normally we are using the ID fan, it should be kept running to avoid any, to refreshing the air. So we are using the ID fan, should be always it is running. In case of any emergency, ID fan is tripped, so we have to stop the work. And this one is some photo from the last ATR, where they are cleaning by using the dry ice by the nozzle. Okay. This table is showing the conversion with the convection cleaning method, which is available before. Dry ice blasting is cleaning is called effort. Compressive cleaning benefit over the traditional method can be saved up to 80% of the current method cleaning. So the table is, the conversion between the method is available. So we have the first one is dry ice. For the dry ice, there is no waste, no secondary waste, non-conductive, non-toxic, and non-abrasive. Another one is sand blasting. Sand blasting is not conductive, not toxic, but it is there is secondary waste and abrasive. For soda blasting, it is non-conductive, non-toxic, but it is abrasive and there is secondary waste. Water blasting, it is non-toxic, non-abrasive, but there is secondary waste and conductive. Hand tools, there is no secondary waste, non-toxic, but it is conductive and abrasive. And the last one is the solvent chemicals. It is non-abrasive, but it is a secondary waste and conductive and toxic also. The safety which is taken while the dry ice is taking place, almost is carbon dioxide is toxic, starting with the high concentration above 1%, and can be display oxygen if equipment is used ventilation of area. So we have always we have to keep the ID fan is mostly running to avoid high concentration of the carbon dioxide while they are working. So we have to make the air is always refreshing, replacing the CO2. In addition, the carbon dioxide behavior heavier than air. So exhaust vent is required to be near the ground level, eventually removing the gas. At the normal pressure, the dry ice temperature is almost -78. and must be handled with the insulated gloves, eye and air protection, are required to be safely as used in the cleaning of the equipment. Compared to the other plastic cleaning method, dry ice plastic products is fewer waste product and does not require the cleaned up plastic method. So the waste products can be swept out, vacuumed, or washed away depending on the contaminant. And this one is some photo from the last ATR, where that's showing the difference between before cleaning and after cleaning, how's the difference between there. And this one also another photo, the same where they are cleaning, is showing before and after. So this one is the change before and after the cleaning. This is in our ATR. Which benefit we are getting from the using of the dry ice. First, it was temperature is 157, and after using the dry ice as in the last ATR, it became 147. So difference is around 10 degree. And before we are facing the problem, we have a challenge that we are using more fuel as a combustion, for the fuel combustion, around 22,000. And after ATR, we are getting around only 20,500 meters cube per hour. So the difference is 1,500 meters cube per hour, and daily 36,000 meters cube per day. And also, we are getting from this temperature, or the temperature pressure, delta pressure became, it was minus 370, and now is minus 325. That means the heat transfer will be better, and velocity time will be less. So heat exchange will be more. We are getting to utilizing the waste heat flue gas temperature to heat the other coils. And the main benefit, we are getting less consumption of energy as a fuel. So saving energy out the fuel reformer burners, return to the fuel feed now, which is ultimately reflect to the higher production. So almost we are getting around roughly 10 to 12 metric ton per day of ammonia by using this one. And this one is some photo showing the difference between and after cleaning. This one is before cleaning and after cleaning. And this one is showing the primary reformer tubes, which you are using, normally you're using the hand cleaning by the ropes. And this one is ما يشتغل فيديو؟ ما شغال؟ There's some video is how it is job is handover. So it is not. ما يشتغل. خلاص الفيديو ما يشتغل. عايز شغال. ايوه ليش ما تصير سيتنج؟ الفيديو ده هذا اول واحد هذا صح؟ ايوه ليش؟ Next. Next. This showing small video how the job is going on. This is the dry ice pellets, how it's crushed by the machine. Then they're using by the nozzle for the cleaning. And there is another video. This is why they're cleaning, how they are cleaning by using the hydrogen, it means dry ice by the nozzles. This is the cleaning method, how they're cleaning. And see the difference, how their cleaning is there, is showing there. Very easy and very safely, and also is costing not that much. So I want to thanks. If you have any question, you can ask.
Assalamu alaikum wa rahmatullah wa barakatuh. Good afternoon, everybody. Today I have the toughest job because I'm the last presentation before lunch. So I hope I'm challenging the smell of the food, and my presentation will challenge the food. So inshallah, you will pay attention to my presentation. My name is Ali Fakhro. I work in Gulf Petrochemical Industries Company, GPIC, Bahrain. And today my presentation will be about the vertical waste heat boiler history in GPIC, our experiences. So the contents, I'll give you a brief company profile, overview of the ammonia plant, waste heat boiler introduction, the histories of our waste heat boilers, inspection, design improvements, the remedial actions we did for the water quality, post-weld heat treatment for the internal bore weld joint, and conclusion. So our company, GPIC, is a joint venture between PIC Kuwait, the government of the Kingdom of Bahrain, and SABIC in the Kingdom of Saudi Arabia. It was established, in 1979. And two great things happened in 1985. First, I was born. Second, GPIC was commissioned. Our products, we have ammonia, which is 1,200 metric tons per day after debottlenecking, and methanol, 1,200 metric tons per day. And in 98, we have the urea plant, which has a capacity of 1,800 metric tons per day. So this is the ammonia capacity throughout the years. In 1985, first we were 1,000 metric tons, then in 89, debottlenecking of 1,200 metric tons, and optimization of the plant gave us, we could reach up to 1,280, and we did a secondary reformer improved design, letting us produce a maximum of one time we reached 1,367. And in year 2012, we changed the ammonia converter basket, which gave us the capacity of 1,345. It is less here than that because in between 2007 and 12, we did the carbon dioxide recovery, which let us get less. They send the PSA gas to that. This is the ammonia process, simple, good design, the normal degassing desulfurization, primary reformer, secondary reformer, HT, high temperature and low temperature shift converters, moving on to the CO2 removal, methanation, and then the ammonia synthesis from the syngas compressor. And this is the waste heat boiler I'll be talking about, which is the exit of the ammonia compressor. These are the types of waste heat boilers. There are the horizontal exchanger type, the horizontal cathode type, and the compact horizontal unit. And the one we use in GPIC is the vertical fountain type. And within this vertical waste heat boiler, there are different designs: basic design, concentric design, and the hot-cold design. The one we use is the middle one, the concentric design, where the gas enters, goes into the tubes, and from the middle, and come out on the side. So this is our waste heat boiler operational features. It reduces the gas from 370 to 240 degrees at 290 bar. It contains 19.5% ammonia, hydrogen 52, and nitrogen 17.5. Boiler feed water, on the other hand, enters the shell at 105 and 45 bar, and exiting as our medium pressure steam at 255 degrees, going to the straight to the reformer as process steam. This is the shell side circular configuration with varying pitch. The boiler feed water heating section is integral. The feed water enters in the sides, both sides of the waste heat boiler, going flows down to the annular gap. It goes up, then flows down here on the sides, entering the boiler generating zone, or the steam with water, boiler water zone, and generates steam, saturated steam, and before leaving goes through a demister. These are just photos of the dummy tube sheet with the sleeve that holds on the tube sheet. This is so our waste heat boiler history. Our first waste heat boiler was done or manufactured by Bellelli, Italy. Its service date from 1985 to 1998, where our first leak was in 96, and then we got 3 more leaks by 98. Second waste heat boiler was Balke-Dörr from Germany, 1998 to 2007. First leak was in 2004, then 2 more leaks in 2004. Our third waste heat boiler was manufactured by Olmi, Italy, from 2007 to 2015. We did not have any leaks or problems with this waste heat boiler. However, the normal issues of thinning of tubes made us have the choice of proactive measurements to replace the waste heat boiler. So we did that also with the same company. So this is our waste heat boiler interconnections. We have from the deaerator, the water goes down to the boiler feed water pump. Within this pump, we have an intermediate section sending boiler feed water to the waste heat boiler, and then the high pressure section goes to our steam drum, main steam drum that cools down the PG cooler, the process gas cooler, exiting the secondary reformer. And these are the interconnections. Of course, we have our steam coming out of the waste heat boiler going to straight to the secondary reformer after mixing with the main medium pressure steam header. This is just a record of the steam conductivity when we got the leaks of the waste heat boiler. So our Bellelli boiler, first 108 days, the leak duration was 108 days. Our conductivity was 251, and ammonia went 565. And then by the end, and 28 February 98, conductivity reached 1470, 48,000 ppm ammonia. And our second waste heat boiler, our first leak, 465 microsiemens per centimeter, and then ammonia 3,000. And then finally, when we replaced it, after taking our measures, of course, conductivity was 30 and ammonia ppm was 17. So after opening and inspecting our first waste heat boiler, we saw that there were thinning down of the walls, failing adjacent to the ferrule tip at the tubes. In the central hot region, this mostly was happening in the central hot region, heavy magnetite powdery deposits, as we can see here in the photos, and discoloration of the tube bundle at the boiler feed water inlet section. And after studies and going back to our to the companies, to our providers, we said that we will plug 58 tubes using the pop-up plug method. There's still photos of the first waste heat boiler. You can see the powdery materials in the first baffle. So for our second waste heat boiler, there had to be, of course, improvements after many years. So the length of the ferrule was increased to 623 millimeters from 462. The MOC, material of construction, was upgraded to Inconel 600 from stainless steel. And the outer diameter decreased to 12 mm from 14 mm. As for the baffle degassing holes, the surface area was increased to 20,810, about 1,000 millimeter squared. These are the degassing holes as the steam exits. Our second waste heat boiler inspection went through several inspections after the leaks. So 2 leaky tubes were found the first time it was inspected, and a total of 16 tubes were plugged. Hydro tested at 65 bar later on, it was found okay. Second inspection, there were no leaky tubes, and we checked, we did the internal rotational inspection for the full length. There was only thinning near the tube sheet. Steam bubbling was done, and the hydro test. Actually, there was one leaky tube by 65 bar. And the third inspection, also no leaky tubes until we did the helium test, and we found one leaky tube. For the third waste heat boiler, the improvements, the IBD intermediate blowdown nozzle was brought closer to the tube sheet, so we don't collect. So there shouldn't be any collection of deposits in between. Size of the degassing holes reduced to 7 mm from 8 mm. Triangular, for the tube sheet, we chose to have the triangular pitch. It was better for our continuous blowdown, and improved the surface finish of the tube sheet, which means I think they did it in a smoother way. And for the shell, the water chamber height was increased by 500 millimeters. For the water quality, the boiler feed water pipeline was upgraded to stainless steel from carbon steel. And we installed the cation conductivity meters in multiple streams to just have close monitoring of the conductivity and the pH of the water and the steam. Installation also of total organic compound meters at multiple streams. It was high in ammonia and methanol plant process condensate due to the formation of formate from methanol. And they could not be removed by the LP stripper and the utilities plant. And for our third waste heat boiler inspection, we did 100% IRIS on all the tubes. 7 tubes were plugged, not because of leaks, just to thinning. And as I mentioned before, proactive decision to replace the waste heat boiler. Fourth waste heat boiler overview, which is the one I was there during the leak. It was supplied by OMI because since we thought that it was the only one that did not leak, so we will go with the same company. It was commissioned in April 2015. And there was a procedural change, as our colleague Mr. Henrik earlier, that we do the post-weld heat treatment under the nitrogen atmosphere. However, 6 months after startup, there was a leak that started. We found from the conductivity that was increasing. And 2 weeks later, the tube failed. And this is the first time we get the leak in the cold zone. So this is the welding failure after we looked through the tubes, poroscopy. I don't know if this is working. Okay. Just a video, but it's okay. So this is the steam and the blowdown conductivity and ammonia content that happened over the days, the 2 weeks, how it increased drastically throughout the weeks. So we had, when the failure happened, it disturbed our plant steam a lot and our gas. So synthesis gas entered the primary reformer with the MH steam. The loop pressure decreased drastically by about 20 bar, from 285 to 267. Indication of the steam flow reformer increased by almost 9 tons. The waste heat boiler PSVs, we have 2 PSVs, both popped. The LTS outlet vent opened 3%, which is the low temperature shift converter. We have a vent downstream, it opened on auto. And as well as the methanator outlet also opened by 7%. So the ammonia vapors entered into the deaerator from the blowdown circuit, which we could not read the deaerator PSV pressure. It went beyond range. And the pH went to 11.04 from 9.9, and conductivity was already high because of our minor leak or hairline leak, but when it failed, it jumped to 51.6 microsiemens per centimeter. So the indication of the MH, of the medium pressure steam, like I said, it increased to 92 tons. So we had to close the valve to maintain our set point. Reformer outlet temperature went up to 805. Our CH4 slip from the second reformer went to 0.56. It's regularly 0.23. Our H2S CO slip went to 2.9. LTS CO slip went to 0.21. CO2 slip also jumped to 2,700 ppm. And this is also, it will increase our methanator temperature, which almost caused a trip. But alhamdulillah, we just had to take our measures to slowly decrease the load on the back end, and we just tripped or controlled trip of the back end. And this is the rate of increase of our ammonia content. And this is the recent leak comparison with the other waste heat boiler leaks, how the 2015 leak, only 6 months in service, and it failed. However, the others could be controlled, the tubes were plugged until we had to replace them. So the post-weld heat treatment for the IBW joints for the earlier for our earlier waste heat boilers, premature failure when the post-weld heat treatment in oxidized condition. They seem to find some scale on the tubes after, which could not be, or were hard to remove mechanically with alkali or hydrojetting. And this scale was settling in the central part of the tube sheet. They cause the lower water circulation and accelerating the rate of corrosion under deposits And the most frequent failure of the tube is just 5 centimeter to 10 centimeter above the tube sheet. So, comments and conclusion, the under-deposit corrosion is predominant in the vertical type. Best water quality is just to keep close monitoring of the TOC and the cation conductivity. The post-well heat treatment, the new method is under nitrogen atmosphere, which is different from the others, which were under oxidized condition. There is no efficient method to remove deposit, but maybe we will see with this new dry ice method, it could help. Easy removal of the ferrules. The hydro test may not identify any minor leak that is there, hairline or less. And also, same as the helium test. Our fourth-way seed boiler, within 6 months, it failed, and we are still investigating that issue with the manufacturer. And we have gone to several meetings. We have cut out the tubes, the main tube that leaked, and another fresh or not affected tube. So it is still under investigation with them. Why did this fail with the new method that they have under nitrogen atmosphere? And once I know, inshallah, I will share this with you. Thank you for listening, and I'm ready for any questions. Yeah.
Last question of you.
Go ahead.
Failure is the Olmi waste heat boiler.
Yes.
It's exactly the same failure of all Olmi waste heat boilers at the moment, not blaming the manufacturer, but this is the heat treatment, what I explained this morning.
Yeah, exactly.
Inside, outside the furnace, and with the hardness value increasing. And this is a typical crack in the world.
In the world, yeah,
so
exactly.
Hopefully this will now answer the question, and the new boilers with other heat treatment will more safe.
But we want to know exactly why, like under nitrogen, why did this? Why is there weakness at this point? Although it is going under nitrogen and being set in the furnace with the...
Yes, the leak at this point is due to the well at this location with heat-affected zone. And if you have the hardness values higher, as I explained in the morning, then you have the hydrogen circulation underneath inside the auxiliary shell, because this auxiliary shell is outside of the furnace. It's cold. We have the right part inside the furnace, which is warm. We have a flowing of nitrogen, refeeding of nitrogen even. And then this area will be affected by hardness values much higher, about 50% higher than allowed. And during operations, that is typical for this kind of boilers now, after a couple of months, they have the leak. And you have a big leak, therefore you have this increase, enormous increase of your values, of the ammonia and so on.
Exactly.
Not comparable to the other figures.
To the other figures, yes. Thank you. Any other questions? Okay. Thank you very much. Thank you.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good afternoon, everybody. I want to talk about a case study for Abu Qir Fertilizers Company, Plant 1, the oldest plant in Egypt. I am Tamer Ahmed Ibrahim, mechanical engineer in Ammonia Plant 1. We have experienced a lot of leakage in the waste heat boiler and the auxiliary boiler, the main boiler of the plant, which the source of the steam for the factory. In 2011, we have experienced low pH boiler feed water. It was about 4.5 pH. It was human being error. It was very bad experience. It was planned to change the waste heat boiler in 2012 because of the old condition and the deterioration of the tubes of the old waste heat boiler. But at the end of the year of 2011, we experienced a lot of shutdown, many shutdowns, and a lot of loss in production because of this case. We have another proof for the pH decrease in the boiler, the auxiliary boiler of the factory. We have experienced an failure because of hydrogen attack in the tubes, the generating tubes of the auxiliary boiler of the factory. And the shape of the failure was window door type, the typical shape of the failure in the hydrogen attack, in the hydrogen attack case. This is the failure shape of the hydrogen attack because of the loss in the value of pH. The typical value is 9.5, and it was decreased to 4.5. So after this case, we experienced a lot of shutdowns in both in the waste heat boiler and the main boiler of the factory. In 2012, we changed the old type of the waste heat boiler with the new type. It is photos for the old type of waste heat boiler in ammonia plant 1. There was a difficulty in plugging the tubes, and we were lose a lot of tubes when we plug the subheaders. Here is the headers of the waste heat boiler, the oldest type. The new type of the waste heat boiler is fountain type. It was very easy to make the pressure test and to make plugging for tubes, but till now there is no any leakage, there is no any problems. I want to talk about the procedure of the change. We changed the waste heat boiler. We started the activities before the shutdown itself. We make a new foundation with a new steel structure for the waste heat boiler. Here is a new foundation, a concrete with steel to decrease the shutdown time. There were some uncertainty and some unprecise measurement in the base plate of the waste heat boiler. So we modified the foundation. We make a frame, a steel frame, and we re-drilled the anchor holes. And there were some some problems in the flanges of the waste heat boiler in the steam or the water side. The water side flanges are tongue and groove, but the supplier get erased face flanges. So we used portable lathe and we modified the flanges. All of that activities were before the shutdown. So we start the activities before the shutdown to reduce the time and increase the productivity of the plant. It is the activities in the shutdown, dismantling the flanges of the transfer line, from converter to waste heat boiler, ammonia converter, and the transfer line after the waste heat boiler to the gas heat exchanger. In that shutdown, we changed the transfer lines for the waste heat boiler. The demolishing for the old one, and it is the erection activities of the new type of waste heat boiler. We also made a pressure test for the transfer lines using blinds and some special equipment, high pressure pump. We made the pressure test up to 526 bar. It was the largest value of pressure test in ammonia plants in Egypt. It is the diagram showing the installation of the blind and the valves and the high pressure pump for pressure test. The equipment and high pressure pump, 526 bar. We also made the boiling out for the waste heat boiler to eliminate the effect of post-weld heat treatment. We made a system consisting of valves and pipelines and a tank and a condensate drum to inject the chemicals. I need to stress about the pH and the chemicals for the boiler feed water. It is a very critical issue. We should consider this thing very much with monitoring all the time for the lab values. It makes us lost a lot of money, a lot of time in several shutdowns from 2011 to 2012. We lost a lot of money because of the hydrogen attack and the pH low value. Any question? Thank you very much. Thank you. Okay. At the same time, when the failure, there is no a reference for the failure shape in the waste heat boiler because we plugged the tubes. There is no indication, or we didn't made destructive test for that. But the evidence, the tubes of the main boiler, not the waste heat boiler. At the same time, there. Yes. Okay.
Sudden operating is the failure.
Yes. The low value of pH caused the cracks or the leak in the tubes of waste heat boiler. Yes. The pH,
I think not good care at this condition. You can use a care of
it didn't exist in the waste heat boiler. The hydrogen attack exists in the main boiler, but the low pH caused a damage in the tubes of waste heat boiler.
At what pH?
4.5. Yes. It is. It was human being error. I said that at first. The main reason for the failures, the low value of pH, and we know that the evidence was very clear in the tubes of the main boiler when we saw the shape of the failure, window door tie. Yeah. Any question? Thank you very much.